Welcome to Contorted Compositions V1 Grasshopper webinar with Radul Shiskov. Let me get my audio. Yeah. Okay. So welcome to the webinar. Glad that you're all here and joining us. This webinar will be roughly about 5 hours. Just some notes before we start. Just a reminder that next weekend we also have 2 webinars, Kinetic Correlations with Houdini and Scripted Synergies with C# and Grasshopper. Please check those out if you're interested and join them if you like. I want to also point out our Simorphine Master's Degree, which is a fully accredited online 9-month master's degree from world-renowned teachers who are all also working in the field and profession from many different offices and industries. And just keep in mind that the early registration and application, which is also for scholarships as well, is deadline is at the end of February. So if you're interested in paying less money and interested in joining, definitely keep mind of that. And if you'd like to learn more, we have our Masters Open Day here. We already did the Open Day live, but the recording is available. Just come here and click Join Now. You'll be able to watch the recording and learn more about the Master's degree. So before I introduce Radul, I just want to make a few notes, a few things. One is our webinars are always recorded and available for 30 days. That information is always on the website and every email correspondence. So yes, the webinar is recorded. You will get access to the recording after the webinar once Zoom processes the recording, and it will be available for 30 days, as mentioned here. The other thing is that, just 2 things to mention, is that we're using plugins for Grasshopper, and one of them, Millipede, is not easy to find online anymore, but we've included it in a link that we've emailed to you all. And I've also put it in the comments, and I'll put it in the comments again. And also, Millipede will give you a message about it's being expired. You can just ignore that message. It's just a message that tells you to update, but there was never another update made again. So just ignore the message. It doesn't affect anything. The other thing that we've put in the Dropbox, actually maybe an hour ago, that we realized is there's another kind of plugin that's not really easy to find, which is called Mesh Tools. That will give you a mesh pipe and a mesh loft, which I believe is used in some of these examples. So if you've already downloaded the webinar files, please make sure just to go back to the link and grab the mesh tools and install that. It's a simple GHA installation. So teaching today, we have Radul, who's been with us for a while. He's an associate design morphine and owner and lead architect at his studio Brep. Radul has completed his PhD thesis concerning application of algorithmic and parametric modeling in the field of architecture design, and is currently teaching as an assistant professor in the UACEG Sofia, which is also our accrediting university for a master's degree. He's been actively practicing as an architect, leading his own studio, designing and realizing various commercial projects such as restaurants, residential buildings, and hotels. Using his parametric design background, Radul participated in the first design morphine workshops in Sofia and got inspired to explore world continental design. Since then, he has assisted and tutored many workshops and led the 4 Children's Foundation interior design collaboration with us. So without further ado, I will hand this over, Radul, if you were there.
Hey everyone. Hello.
Hey, we see you.
Thank you all for joining the webinar. Thank you, Mike, for the introduction. So I think we should start now.
Yeah, share your
Yep.
screen and then feel free to turn off your camera as you're teaching to save resources. And I will be here in the background trying to answer questions. And if you need me, just call me out. I'll be here.
Thank you. So I hope everybody downloaded the files that we sent earlier. This webinar will go as follows. We'll go through all the definitions that I sent you. I'm going to explain all the steps here, and feel free to ask questions, and me and Mike will do everything we can to answer them. So as an introduction, we're going to use basically a few periodic surfaces and we're going to morph them into some complex geometries, and we're going to further iterate those geometries into some designs. The periodic surfaces are really nice because they can fill up space, and they work pretty neat with the twisted box geometries, since we can fill any space and shape with twisted boxes, and then use the periodic surfaces in them. The first step here in the first file, periodic surfaces, it's called, contains a few definitions. We're going to start with some introduction to Millipede. We're not going to use it its full potential. We're just going to use it for the creating of some periodic surfaces meshes. And here I have some formulas for periodic surfaces. By the way, you can do your own research on them. They're pretty popular on the internet. There's this nice site where you can check more information about them and see their topologies. Unfortunately, none of the surfaces formulas are uploaded here, and those here in the panels, we're going to use them to recreate some of the periodic surfaces. For this purpose, we're using Millipede, and it basically needs, sorry about that. So in the first component here, I've plugged all the formulas for different periodic surfaces, so you can easily scroll through them and change the input for the Millipede. This here basically goes into the evaluation component, and it gives a value from each of the mathematical formulas here. In order to do that, first we need to input some x, y, and z values for that expression in order to be calculated. And in order to do that, we need to make a set of input parameters in 3 dimensions. The periodic surfaces their periods are always between minus pi and pi. That's why we're going to start by dividing the minus pi and pi domain into a range of numbers here, and that will give us a list of numbers that we're going to use to cross-reference and basically get this set of points or values that we're going to use for the evaluation of the different formulas. Cross-reference, that makes pretty much a permutation of all the inputs here in ABC. So if we input here a list of 15 numbers, it's going to output 3 lists of 15 on the third power numbers. So basically that's a set of numbers or points with coordinates between minus pi and pi. So we're inputting those lists in the evaluate component, and we're going to use those values for the Millipede component isosurface here. Another thing we need is a bounding box where the geometry will take place. So we're just going to make a simple box, square box will be best, a cube. And we need to input the resolution here in X, Y, and Z. But before that, we need to input the X+1 values here, because when we divide the range into, let's say, 14 steps, that obviously gives us 15 numbers. So the resolution here and the X, Y, and Z needs to be the same as the initial input of numbers. So the isosurface component takes the values from those points that we earlier make. Basically, each point here goes with a certain value that corresponds to the mathematical function of the periodic surface. And the isosurface component makes a mesh that connects all the points with a certain ISO value here. So when we plug some value, let's say needs to be actually 0 for the minimal periodic surfaces, but or something really close to 0 in order not to crash it. This component makes a mesh that connects all those values that are equal to 0 or any value here as a parameter. And those values are a function from the mathematical formulas here as input, each separately. So once we have this setup here, the output is this mesh, you can see, and by changing the stream gate index here of that filter component, we can go through different periodic surfaces. Some of them you can even explore further by changing the ISO value here and see some weird geometries as a result. The resolution of the mesh depends on that initial parameter here. That the higher the number, the more refined the mesh is. But you need to be careful with that in order not to make the geometry too heavy. So one problem with this approach here is that, as you can see, the topology of the output mesh is not really perfect. Like there's those really small and weird faces, and we can work with that, but it would be better if we fix that topology in a better way. So basically, that's just the Millipede part here. It's not much. We just use this isosurface component, and we use this list of mathematical formulas. You can do your own research. If you find some more expressions, feel free to share. Here, I have some of them, and I don't remember all the names, but it's a really big topic, and you can read some papers about it. So after we have this setup, we can choose any of all those periodic surfaces to work with for our further design. As I mentioned, we will really need to fix the topology of those meshes and refine them, because that will give us the opportunity to use it later as patterns and a more precise geometry. In order to do that, it will be best if we are able to translate this mesh into NURBS surfaces. Now, the new Rhino 7 has some really awesome new algorithms that can make any mesh into sub-D and then into NURBS geometry. But here I'm going to show you a few approaches when we do this step by step manually, because in that way we're going to have a better control on the topology of the surfaces. Basically, what we want to achieve from here is to turn this mesh into NURBS geometry. And how are we going to do that? Here we have the mesh, and if you look at it, you can see that there is some rotational symmetry in it. So if we manage to just make a small part of the mesh into NURBS, then we can just copy, rotate, and mirror it, so we'll get the whole surface. In order to do that, we can split the mesh and find this the smallest part that repeats itself. So, by the way, okay, so we do that by taking the bounding box of the mesh first. And in the center of that bounding box, we can make XY, XZ, and YZ plane, and use those plane in order to cut the mesh into 8 parts. Because as you can see here, 1/8 of this mesh repeats itself with a rotation and some mirroring in order to get the whole mesh. When I was doing the tutorial, I found out that the Rhino 7 here has some problems with this mesh split component. Basically, it doesn't output the correct result. So if you're using Rhino 7 here and you're not getting this 1/8 of the mesh after splitting it, just use this internalized mesh here. And you can continue by changing the input from the mesh split to this mesh here. And how do we get to this mesh split? Like I said, we place the three planes into the center of the bounding box of the mesh, and then we use the mesh split component in order to split the mesh into 8 parts that repeat itself across the mesh. So the next part. So if you manage to turn this 1/8 of the mesh into NURBS, you'll be easy to make it the whole surface into NURBS. So we're going to do the process. We're going to use the initial mesh as a guide mesh, and we're going to use the edges of that mesh, including some additional inner edges, to turn it into NURBS surface. And once we do that, the same process will be used to turn the whole mesh into the NURBS surface. So for now, I'm just going to work with that 1/8 of the mesh here. What I need is to take the naked edges of that mesh here with the naked edges component from Weaverbird. And then turn the edges into a smooth curves, add some additional inner edges here, and make the surfaces that create this complex surface. So what I'm trying to do is take
Hey, Radul,
Cool.
do you want to just for a second stop?
Yep.
I don't know. There's a few people that just don't seem to understand how to install Millipede. So basically, from the libraries folder, you have to go to File, Special Folders, Components folder, right? And then
Yep.
you have to drop everything from the libraries folder into there. Millipede.gha, millipede shared.dll, solvepansolver.net, net.dll, solvepan statica.dll, solvepan statrhino.dll. So that's 1, 2, 3, 4, 5 files. They all need to go into the. So you just copy them like that and paste them into the folder there that you see.
Copy them and paste them into your libraries folder in Grasshopper.
Yes, and then
I'm not gonna replace them, but you just
and then
paste
you'll
them.
and then you'll likely have to restart Rhino Grasshopper.
Make sure you unblock all the files here, because sometimes you need to unblock all the 5 files here from properties, and then just drag the GHA file into Grasshopper and see if it works. And if it's not, just restart and try it again.
Can you send them the URL of this minimal surface? Otherwise, they'll never stop asking for it. They would just keep asking for it.
Sorry, the website? Yeah,
yeah.
sure. Okay, where is the chat? Sorry.
Hunter, I'm not sure why it's not working. I just tried it again on a Rhino that I didn't have Millipede, and from this files Radul provided, and it's working fine. So I'm not really sure why it wouldn't be working for you. Yeah. If like I mentioned, Millipede will give you a message that it's expired, but it's not really expired. It's just a message. Just ignore it. It's just because it was on a release schedule before where it used to expire, and it used to just basically be telling you to update to the newest one, but there was never another update, so just ignore it.
Okay, so I just pasted the URL in the chat.
Yes. And yeah, for all other plugins, if you download them from Food for Rhino, make sure you unblock the file. You just right-click it, Properties, unblock file if it's blocked. Mesh Tools, Jose, Mesh Tools is working. Okay, so Mesh Tools and MeshEdit do not make their own tab. They get put throughout Grasshopper in the default tabs. So you'll know Mesh Tools is working if you search something like Mesh Pipe and it's there, you're great. They do not get their own tab. So Mesh Tools and MeshEdit do not get their own tab. They get put in the native Grasshopper tab throughout. They don't get their own tab. How can I preview Rhino image? Yeah, you just right-click components to preview on preview, and then or you can click that button.
I'm working with this button on, so it only shows whatever I select, because it gets really messy otherwise when it shows all the geometry.
And then some of them are asking if you can switch to icon view. I don't know. That's up to you.
Well, it's going to take. Okay, really?
Yeah, I don't. For me, if you like it that way, it doesn't matter.
Well, I guess half of them are going to use to the icon menu, and the other half are used to the.
Yeah, just teach the way you want, as long as the bifocals
I'm
are
used
there.
to this because it takes less space, and the bifocals shows you the names of all components here. So if you just wonder any component, just type whatever it says here above the component.
Yeah. All right. Well, I'll let you get back to it then.
Okay, so we were here. We're trying to turn this mesh into the nerd surface. In order to do that, we're going to add, just bear with me here, a few more edges into it, and then we're going to make edge surfaces from each 4 edges. And all we need to do after we take this naked edge of the mesh is to split it into 6 separate edges and then add those 3 additional edges here in the middle. And we're going to do that by following the initial mesh as a guide mesh. You see what I mean in a minute. But first, like I said, we need to split this naked edge into 6 separate splines. So okay. Here I'm just first sorting the list of naked edges by area in case there's some bug in the geometry and get some really small naked edges. That's why you need this sometimes. So that gives us this naked edge of the mesh. And here we're taking all the points, the control points of this polyline, and we want to check which of those points are the inflection point of the polyline. So the corner points of this naked edge, they belong to this wireframe of the bounding box here. Sorry about that. Okay, so need to go a little bit further. We need to take the 8 bounding boxes of those meshes, take just the edges from them. We're gonna see which from the points of the naked edge here belong to the corners of the bounding box. So we are testing the control points and the distance to them to the edges of the bounding boxes here. And the closest points of those are the, like, if the distance of any of those points is less than 0.1, we know that the point belongs to the one of the wireframe here. In this way, we get the pattern to dispatch this list of points and just get the corner points of this polyline here. And after we do that, we can use those corner points to shatter that polyline into 6 segments. So here first, we need to kill some of the points because they may be overlapping. And then we're going to find the closest point from each point to the curve. And we're going to use this parameter to shatter the curve at that point. And that will give us 6 separate polylines here, as you can see, which we can then rebuild and make them into smooth curves. So that's the first part. We made the naked edge of the mesh into 6 separate smooth curves. The next part, we need to add those inner curves that create the complex surface. And how do we do that? First, we need to add this middle point here, where all the surfaces connect. And this is done by making an average from the list of the corner points here. So the average point is the center point of the whole surface, and we want to find that point projected on the mesh here, on this initial mesh. So that in that way we make sure that all the points we are using, they're part of that initial guide mesh here. So we need to project all the new points that we are making on the initial guide mesh. So once we get this point, okay, and the naked boundary here, we can make lines from those 3 corners to the center point. In order to do that, first we join those 6 curves, and then we find the discontinuity points of that curve, and then dispatch them in order to get just 3 of those control points. And then we can connect those 3 control points to that center point here that we make on the mesh, and we get those three lines here. So the next step is we need to project those 3 lines. We need to make them part of the mesh. So right now they're just align segments, and we need to project them on the mesh. So we divide. I'm going to just turn off this for now. We divide those lines into 3 points, start, middle, and end, and then we project those points into the mesh, and then we interpolate again. In that way, we get these smooth curves that we know it belongs to the initial mesh. So that was the second important step. And once we have that, we can just make edge surfaces between the 3 sets of 4 curves. So we need to make edge surface between those 4 edges, and then edge surface between those 4 edges, and then again here. So how do we just know which how to list them? That's kind of tricky because we really don't know the order of the items, so it takes a little bit of guessing, but it's important the logic behind it. Basically, we divide the mesh into 3 4-edge surfaces here. So,
hey Radul.
Yeah.
Actually, I realized something. So a lot of them were saying that the Rhino 7 isn't working, and I think that's because maybe they missed the mesh split part.
Okay, I'll go back.
Yeah, so if you want to just explain that.
Sure.
So if you're having errors, there's something Radul will show you, because we found actually like recently that for some reason the mesh split in 7 has a bug, and we reported it to McNeel. So Radul provided the mesh as an output there, as you see on his screen. So you'll want to use that instead.
The Rhino 7, the component here, mesh split in Rhino 7, doesn't work quite well. Here we have the input mesh, and we try to split it with those three planes. So you should have as an output 8 separate meshes here, because the box basically is split by 3 planes, and that should give you 8 meshes. But for some reason, the Rhino 7 doesn't have this output. It gives some really weird mesh here. So if you are using Rhino 7 and you don't have 8 meshes here, but something like 50 or something like that, just use this here. That's the internalized mesh that I did. That should be the output here from this mesh split component. So if you're using Rhino 7, just change the input here from the mesh split into this internalized mesh. Does that make sense? Should I wait a few minutes then for everybody to catch up with this part?
That makes sense. I just did it as well, and that's cleared everything up.
Okay.
But I plugged it into the naked boundary. I think you have it into the list item on there.
Yeah. First, I'm going to do it just with one
Yeah.
part of the mesh, and then we're going to change the output here for the whole thing
Yeah,
at the end.
so
Just trying
again,
to explain the workflow here first.
yeah. So if anyone has that issue, it's just something out of our control that McNeel needs to fix for the mesh split component.
So if you're using Rhino 7, just change the output from the mesh split component into this internalized mesh that I provided. That's basically the splitted mesh here. It contains 8 meshes. Okay. Should we continue? So
yeah, I think we're good. I see them
yep.
saying that it's good now.
Okay. So we make those 3 surfaces here, and their topology is it's really good because it's a 4-edge surface. We can easily make it into a UV surface, a UV mesh. Sorry about that, and then join it and have this mesh with really nice topology that we can further edit. So if you are up to this part here, we made the surfaces for just 1/8 of the mesh, and the whole idea works pretty good if we input those 8 meshes here in the naked. Like right now, I just did it for 1. That's why I used the list item component just to show you the logic behind it. But after splitting the mesh into 8 parts, the same logic can be applied. So when we plug this list of meshes here, by the way, it should be grafted if you don't flatten it or something, and don't forget to graft here. If we plug the mesh here into the naked edged component, the output at the end should be a whole NURBS geometry of this initial mesh. And the whole mesh now is consisted of these 4-edge surfaces. They're untrimmed, so we can remesh them as we like and change their resolution and further work with it. And you'll see later how the patterns that we're going to apply really depend on the topology of the mesh here we're using. So after making it into untrimmed surfaces, we can mesh it and then join the mesh with the Weaverbird mesh join. Don't forget to weld the vertices here. And then later we're going to further smooth it and apply some patterns and so on. So that was an example of how to change the topology of this mesh here that is outputted from the ISO surface, which is really bad, and make it into this really nice quad face mesh that we can further work with. Let's do another example. That's, I think, another of the meshes here. I think it was called it was here in number 2 of the list, which is the shared surface 2. So basically, the logic behind it's the same as the previous one, but this time we don't have a rotational symmetry. We have symmetry on the 2 planes here. Other than that, the logic is similar as the previous one. First, we split the surface into the mesh. I mean, into the meshes that are consisting, that are making it. The same applies here, by the way. If the previous component on Rhino 7 here, the mesh split doesn't work, it will give you some weird outputs here, like not one and one mesh, but many. So if you're using Rhino 7, use this internalized mesh here instead of the A output, and this internalized mesh here as the B output. That's the two parts of the mesh. Like we are again splitting it with XY plane, YZ plane, XZ plane, and we need to do that a few times. So first you get those two parts, and then we split them with the YZ plane in order to get those two parts. And then again, if you're using Rhino 7, change the output from this component mesh split to that internalized mesh here. Is the same. And then we're splitting it third time. Then again, for Rhino 7, just use this internalized mesh here for the next component. So the point is we need to get to that basic mesh that makes the whole mesh. Like if we have this, if you make this into NURBS, then it's just one mirror here and then another mirror here, and we get into the whole mesh. So we're working with this part. Again, we take the naked boundary. Actually, those are two meshes here. Sorry about that. It's not one. There are two because they're kind of different. Not really, but like it's better to work with those two meshes rather than trying to rotate the first one above and then mirror it. So the logic is same as the previous one. We take the naked edges and you want to make NURBS surfaces from those contours. In order to do that, we need to add those inner curves, and then make edge surfaces, edge NURBS surfaces. So take the naked edge. Again, we take the control points. We check which of the control points belong on the wireframe of the bounding box by measuring the distance from each point to the edges, and then using this as a pattern to dispatch the points and get just the corner points of each polyline. Then we use those points to shatter the curve and then rebuild the segments into smooth curves. Then again, we rebuild, and those are the outer edges of the NURBS surface. In order to add the inner edges, again, we connect three of the corners with this center point here on the mesh. We divide those lines into segments. We project the points on the mesh, and then we interpolate. So we get the new curves in a way that they belong to the initial mesh here. By the way, I know I'm running kind of fast through all of that, but we have a lot of stuff to cover, and it's important for you to just understand the logic behind it, and later you can go through all those components one by one and understand them. Right now, you don't need to remember all of that. It's important to follow the logic so you can later look at all the components and how they work. The point is, again, we make edge surfaces from those curves, and those are really nice NURBS surfaces, untrimmed NURBS surfaces. Once we have this, we go back from here the same way as we split the initial mesh with the XZ, YZ, and XY plane. We can go back and then mirror it once, and then mirror it again in order to have this final surface made of untrimmed surfaces. So that was the whole point, to get here from here, that we are fixing this really bad topology and we are making it from NURBS untrimmed surfaces that we can later again remesh the way we like. So once we have untrimmed surfaces, we can always mesh those with the necessary resolution and join them, and of course then smooth it additionally or apply some other algorithms to them. Those two examples we're going to use later for some of the designs here. Here I'm just adding a few additional steps of editing the meshes here from the NURBS surface here that it's consisted from 24 NURBS surfaces. We can mesh them with the mesh UV surface, join and weld them. And then don't forget to unify the normals, because otherwise some of the faces are going to be faced in the opposite direction from their neighbor. Once we work with those quad meshes, we can apply additional smoothing algorithms from Weaverbird or MeshEdit or any other plugins, and work with that from there. But we're going to show how to edit some meshes in the next file that I sent. So those were two examples of how to make a periodic surface with Millipede, and then make it NURBS and change the topology with some additional steps. And that's really important, as you can see later, because it will help us apply patterns and edit those surfaces in a better way. That won't be, we won't be able to do that if we work with this topology. Another way to make periodic surfaces, except from using the mathematical formulas here, you can do your own research and find some other topology to fill the space. For example, I really like, just give me a second here. I found on the internet this periodic surface. It's again based on a box, and it can fill space in three directions. I did a little research on it, and it's based actually on a truncated octahedron. So here I'm going to quickly show you how to build this from scratch and build it as a NURBS surface. I don't know the name of the surface. I couldn't find it on the internet, but I guess there are many similar to this. So you can do your own research and try your own ways for creating other periodic surfaces. But for this one, like I said, it's based on a truncated octahedron. This component is from the, what was that, Lunchbox, I think? Yeah. So the truncated octahedron, it has this parameter here. That's a platonic octahedron, just two pyramids stick to each other. And when you truncate it with a value of 1 here, it becomes this shape. And turns out that it's the easiest way to create the surface that I show you is to use this truncated octahedron. But first, because when you truncate it with a value of 1 here, as you can see, this component gives you invalid BREP for some reason. So before further using it, I'm going to rebuild it by deconstructing it and then just joining the faces again in order to make a closed BREP here. Like it's the same like this, but this gives invalid geometry for some reason, and that's just one closed BREP. And this part here is just to orient it in a proper way. in order to visualize the surface better. Like we need to put it with the triangle face on the ground. So I'm just taking one of the triangular faces and using its frame in order to orient the whole thing like this. And if you pay attention to the surface, it's actually, it feels this truncated octahedron in this way. It goes, okay, I'm just going to bake that. By the way, I forgot to mention, I've sent you the layers and materials Rhino file here. There's no geometry in it, so basically you don't really need it. But here I prepared some of the layers and the materials that I'm going to bake into, so it'd be easier for you to use this and bake geometries into layers with already preset materials. So that's the surface, and it's contained in this truncated octahedron. And the logic behind it, it's just constructed from those, how much is it? 6, I think, 6 surfaces. So we're going to use this wireframe here from the truncated octahedron in order to make the 6 surfaces that create this periodic surface. So first, we only need to work with the faces that are triangles. So I'm dispatching all the faces from here with a pattern that tells us which one of the faces have 3 control points. So discontinuity, this length, and we're checking if the least length here is equal to 3, and that gives us the pattern to dispatch the faces into those only triangular faces. Next, we need to, just a second. We need to work only with those triangular, those edges of the faces. So those components here, they basically kill all the horizontal edges from here. So I'm taking a point on each edge, and I'm checking if the z coordinate of that point is the same as the start at the end point. And by doing this, I'm getting a pattern for culling the horizontal edges from here. So basically, I'm dispatching the list of edges from those triangular segments into horizontal ones and those that I actually need for making the surface. So that's one part of making the surfaces. The other part is again adding those additional edges that connect into the center here. So adding those 2 lines and those edges, we are making edge surface from each 4 of those edges here. That gives us those 6 NURBS surfaces that are creating this whole big periodic surface. And to visualize it better here, I'm orienting it in the previous way in order to fit better into our rectangular bounding box. So when you do it like this, you can actually see why this is a triply periodic surface, because if you add the same surface on the X, Y, and Z direction, it's going to smoothly continue to the next one in the 3 directions. So again, that's a NURBS. It's constructed from untrimmed NURBS surfaces that we can easily make into a mesh and remesh again, and then edit it. It's not necessary to always work with a really high resolution meshes. like we can make this UV mesh from surface with really big resolution, or we can just make it with a small resolution, let's say 2, and then join them and further smooth it with some Weaverbird algorithms. And that's what we're going to do next. We're going to morph this mesh, this wall poly mesh, into some twisted boxes, and then additionally smooth it and see what geometry we're gonna get. So I'm going to use this mesh here, the result with really low resolution. I'm just going to leave this UV values of the mesh on 2. And I'm going to, or maybe we can just morph the untrimmed surface first into twisted boxes and then mesh them. So next step of the process would be creating some twisted boxes where we can morph any of the periodic surfaces into. So if you're not familiar with the twisted boxes, there's this great plugin Pufferfish, which gives you a lot of different ways of creating twisted boxes. Basically, you can use a lot of ways for that. You need to pick it accordingly to the geometry you want to achieve. Here the point is, I'm going to use this periodic surface that I made to create this design here. Maybe you've seen it from the promo material. That's this surface morph into some twisted boxes and then further smoothened and articulated with some pattern. So we have the first part here, the periodic surface that we're going to morph. Now we need to make some twisted boxes, and the way I've decided to do them here is to make them between 2 surfaces. We can make 2 surfaces with similar topology, and then we can make twisted boxes between those 2 surfaces. And after that, morph that periodic surface into those twisted boxes. So there are many ways to create those 2 surfaces that we're using for the twisted boxes. You can make them from scratch and then just play with the control points here in Rhino. Here I'm going to show you a quick, I think, interesting way how to make them algorithmically. It's just one example, but you can use your imagination and your experience to model those 2 control surfaces for the twisted boxes, basically. So here I wanted to use another mathematical equation for one of the surfaces, for the upper one, and I'm going to use some Grasshopper scaling for deformation for the surface in the bottom. So let's start with the upper surface here. We just make a simple square, divide it into UV points, and we're going to use the X and Y coordinates of those points for this expression here, and that expression is going to give us this surface. And along the way, we're going to add some parameters that control that surface. Basically, you can look for some other equation for surfaces. Again, I don't remember the name for this one. I found it somewhere, but there are many different mathematical equations that give some really beautiful surfaces here. So we're using the X and Y coordinates from this list of points here. Here, maybe we need to divide the values a little bit in order to make it more manageable. We plug the X and Y values in this equation, and we add these initial Z, U, and V parameters that control the surface. And then we use the result here with the coordinates of the initial points, but plug the result in there for their z coordinate. So that gives us a visualization of this function here according to the parameters that we've plugged in. And after we get those points, we just interpolate with curves and then make wafts from those curves. And those parameters, they control the amplitude of this function. And you can also, I'm just going to unplug this here in order to change some of the, okay. So we are working now with this surface. The initial point that controls the position of those points also is a parameter for the function because it changes the x, y, and z value for those points. So you can explore how the function evolves in the coordinate system. And there are some the parameters for z, u, and v in this function also give some different inclination, and that's the scale for the z coordinate of the function. So you can play a little bit with this, but in some point, of course, you can just bake the thing, rebuild it, because you're going to be with some values, and then manually change it as you like, and then plug it back in Grasshopper as a control surface here. Oh, sorry. So that's an example how to do the upper surface, and this bottom surface. I wanted to have this shape because I'm trying to make like this space here under the future geometry, like a dome. So in order to do that, I'm using again those initial points, and I'm using their average point as an attractor point, and the distance from each point to the attractor point I'm remapping with the graph mapper into certain domain, and then I use the values to move them in the z direction and rebuild this surface from them. So here the graph mapper is some controller here, and those values of the control domain also. And you can explore different graph mappers. You can play with geometry, and of course, at any point you can just bake it and remodel it as you like. So those two surfaces that I make, I use them first a little rebuild surface for to make them smoother and nicer, and then those two surfaces here I use for making twisted boxes between them. That's twisted boxes through surfaces, and it takes a set of surfaces, and it needs a range of parameters in u, v, and w direction, and that gives us a set of twisted boxes. By changing the steps in the range here, you change the number of twisted boxes in the 3 direction, so we can play with that as well. And the point is, once you have that, you use those twisted boxes, like right now they're 18, to morph this periodic surface that we made into those twisted boxes. First here, I take the NURBS surfaces and I mesh them with a raw resolution of 1. Just make a simple meshes from the surfaces, join them and weld them, and then I use this mesh and morph it into this set of twisted boxes here, and the result looks like this. It's kind of hard to tell what's happening here, but once you smooth it, like maybe I'm just going to lower this parameter here, make it just 1 layer. So the result here is this list of meshes, 9 right now. After joining them and welding them, we can now, of course, unify the normals. We can smooth this mesh, sorry, with a Catmull Quark algorithm, and it's going to look more as we want to. So yeah, so that's basically a wall poly modeling. We're morphing wall poly meshes here, and after welding them, we can further smooth it and then edit it. Also, you can again split the mesh here with some XY plane. If you want to cut the bottom of it, again, the mesh split component won't work on the Rhino 7. But I think I didn't actually have this mesh here as an internalized output. So if you're using Rhino 7, just don't use this mesh split, but just use this mesh here into the unify normals. So if you're using Rhino 7 here, just ignore this component and use this as an output here, as an input. And if you're using Rhino 6, what I'm doing here, I'm just splitting the mesh with some XY plane with a parameter of control point as an origin. So you can move the point. It's kind of heavy because there are other components after that. But the point is you can just cut the mesh wherever you like. And this part here, because as you can see, if you cut the mesh, you might have some faces like this that are not actually part of the mesh anymore, but there still are. Sorry. So here I'm just getting rid of this face here by taking the naked edges and seeing which one can be found, for which one you can find a centroid, and then basically compare it with the other centroids and call the index, find the index of that face and call it with the delete mesh faces. If you're using this mesh here as an input for the unify mesh normals, you won't need that part because you're not cutting the mesh. But if you're using the mesh split and you have some meshes like this cut improperly, you're going to need this part in order to delete faces like that. So I won't go too deep into it. You can check that later. This part just deletes faces like this if you cut the mesh from the bottom. And once you're done with morphing the mesh here, you can again smooth it with Weaverbird subdivision and some Laplacian smoothing. Yeah, you can use also a Catmull Quark algorithm if you want to keep the quad faces, and then use the Laplacian smoothing. The Laplacian smoothing is relaxing the mesh, but I'll say more about that in the next chapter. The point of this chapter here was to get to this part, this wall poly mesh that we're going to further edit in order to get to this. So another thing, that wall poly mesh, you can always bake it and then turn on the control points here in Rhino and change some of the positions here of them, and after like edit it manually, and then you can input it here in Grasshopper again, and of course do whatever you like with, like, smooth it further. So if you feel like your geometry needs a few touches, you can bake this wall poly mesh, edit the control points here, and then go back with it in Grasshopper and continue with the workflow. Also, what you can do with that wall poly mesh, you can turn it into sub-D, but I'll show you that in the third chapter. So let's say we're happy with the result so far with that flow polymesh, and we want to continue by further editing it, editing the mesh. What I forgot to mention is another workflow here. Another thing you can do is use the mesh mirror cut right here and experiment with some positions and rotations of the mirror planes in order to get some other meshes, and that can look really nice as well. So this wall polymesh, we're using an input for the mesh mirror cut, and here you can experiment with different positions and planes and their rotation in order to get some really different results from that mesh. Like for example, okay, I'm just going to put this here, this mesh. I'm going to bake some results from the mirror cut to visualize what I mean. So adding those mirror planes gives you a lot of agility in how to achieve some complex geometries. That concludes the first chapter of creating and morphing the periodic surfaces into the twisted boxes. And the next chapter is going to be the editing of those meshes. So right now, I can answer some of the questions maybe so far. So if you have any questions from the things that we covered so far, now's the time. I get an area fault before clean tree after webbing making boundary. Okay. I see now Mike is answering most of your questions here.
If you just go to the open tab, there's some questions there that are like, I didn't.
Sorry, which tab?
Open. In questions and answers, there's like open,
okay.
answered.
Is there a reason for using NURBS? Why not reconstruct the old mesh into a cleaner mesh workflow? Well, for me, that's the cleaner way to the cleanest mesh you can get is to going into NURBS, into untrimmed surface, and then making it UV meshes from those untrimmed surfaces. Like I said, the new Rhino 7 have some really nice commands for making sub-D geometries and then making it NURBS. But I think the algorithmic approach has a little more control over the geometry, and I think that's the you can get the cleanest mesh by going through this. My surface equation expression box gives an error. Or right after that, any idea why? Your surface equation. Does that mean it's not working in the file that I sent, or did you change something here? Are we talking about this surface equation actually? Expression, or this one? Well, make sure you have this gate parameter here on some value that actually exists in the list. I guess other than that, really not sure why it wouldn't work. I get an area fault before clean tree, after weaving naked boundary. Yeah, so that's the mean here, because this naked boundary, it will give you the area only for those faces that are actually triangles. You won't get you the area for the rest of it, and those were the ones that we actually want to kill. So that's why I'm looking for the center, and that's the only geometry that you can find a center for, and that's the phase that we want to kill anyways. Yeah, curves must be planar. That's the point. We want to kill only those that are planar, because those are going to be the ones that are disconnected from the rest of the mesh. So if we're talking about this area here, that's supposed to be red. That's not a problem. That's actually what we want. We want to have only this here in order to delete it.
They're saying something that I don't understand. They're saying Radul said plug in mesh unified normal into another mesh unified normal if you're using Rhino 7. I don't know.
I said to plug the internalized mesh, maybe.
Yeah, you'd plug the internalized mesh. Like you wouldn't plug a unified normal into another unified normal. That wouldn't really make sense.
Okay, yeah. I'm using here the unified normal because the mesh split maybe gets the normals wrong. So yeah, they're actually right. If you don't use this mesh split plane, you don't need this unified normals as well. Just continue. You can change the input from here to this unified normals as well. You need this unified normal after you split the mesh, and that's just in case, actually.
Yeah, but you're not plugging a unified normal into another unified normal.
No, I said for those who use the Rhino 7 to skip this, because I don't have the internalized mesh here. So that's why I just use this input for here, but they're right. You can just change the input like this from this unified normal to those.
Yeah, so just use one of them.
Yeah.
Because I think if you put one into the other, it would break.
Yeah. Thank you. Okay. And if you skip this part of splitting, and you won't need this part here for deleting the faces as well, because you're not actually cutting any of the mesh in this case.
Yeah. Got it. Yeah.
Okay. So let's go to the next file here, the one with the mesh edit. Like, let's say we're happy with the result from the mesh morphing in the previous file, and we end up with this wall poly mesh. We're going to further edit this mesh in order to achieve the design that I showed earlier. So that's the input part, the input mesh for this part. I'm going to show you a few different ways how to edit the mesh and make some skin openings and stuff. So first of all, the wall poly mesh can be really nice smoothened by the Weaverbird Whoop subdivision or Weaverbird Catmull Quark. The smoothing, the difference between two is that the one triangulates the faces of the mesh, and the other keeps them as quad faces. So the topology of the mesh, it's going to affect the pattern that we can apply on it later. So let's first look at the workflow for working with triangulated meshes. First, we're smoothing the mesh with Weaverbird loop subdivision, and then we're using the.
They're still having an issue here. I don't know. Maybe do you want to save that file with removing the unify normal, whatever, like as another file, and I'll just give it to them because it seems maybe they're just not understanding that part.
Okay, we don't need all of that here.
Yeah, maybe just like do the edit you're saying and then just
So
put it.
After morphing the mesh into the twisted boxes, just join them, weld them, unify the normals, and then you can further either use the mesh mirror or straight into.
You want to save this as like an alternate file? And just I'll send it to them or something.
Okay. Should I send it now?
Yeah, if you wanted to send it to me.
By the email? Or can I drop it somewhere here?
I think you can put it in Dropbox.
In the Dropbox?
Yeah.
Do I have the link?
Yeah, the one that we're working on. Well, maybe, I don't know. Just send it to me email. It's fine. Just send me a quick email or something.
Okay, I'll just stop sharing just for a second. Just a second. Okay, done. So Mike is going to share the edited version of the definition here, but it's not that important because everything from here I internalize the result, and you can just go to the next file and continue working with this internalized mesh here. Okay.
Did you send that to my email?
Well, to the email that I sent the definitions yesterday.
Okay. I didn't receive anything yet. Ah, got it. Okay, cool. Thanks.
So we're working with this wall polymesh, and we can smooth it with Weaverbird Catmull Quark algorithms. And the ablation smoothing is kind of like relaxing the mesh a little bit. The number of iterations here don't affect it that much, but they can increase the time a little bit. And as you can see, we have some nice topology here. I'm just going to turn this on. Yeah.
They're asking if you could turn on the bifocal.
Oh yeah, of course. So we end up with this smooth, nice mesh, triangulated. And the first step would be to one of the characteristics of the periodic surfaces. They have like two faces that are facing. So if we offset this initial mesh this mesh here. Let me smoothen it. We can offset it using the offset mesh. So we have the two faces of one mesh. We can enable those in order to look at them. So we have those two faces, and in order to make them look connected, I'm going to make a pipe that connects the two inner and outer surfaces here first. So after offsetting the mesh, here we have the two meshes, and if we take the naked edge of this initial edge, it's the edge that goes just in the middle between the two meshes. And when you make a mesh pipe with a radius equal to the offset distance here, we can visualize this smooth edge that connects the two meshes, the two faces of the mesh. Yeah. So next step, we need to apply some patterns on one of the faces by choice. In order to do that, we use the topology of the mesh itself. So there are some different ways to change that mesh and into having some interesting pattern on it. For example, if we use this Weaverbird inner polygon subdivision component, it just triangulates the mesh in this particular way, and we can just give it some thickness and maybe, okay, let's say make something like that. So that's a possible result. That's just Weaverbird inner polygon subdivision, and then give it some thickness, and we applied this to only one of the mesh sites. So that's one possible result. Another way of dealing with it is subdividing it further with the Catmull-Quark algorithm, and that will make a quad faces from the triangular faces, which is the case actually in this design. So as you can see, here we made some openings with some different openings with different depth, and that comes from the Catmull-Quark algorithm of subdivision. So first we subdivide the triangulate mesh with Catmull-Quark just with level 1, because we don't need that to be really small pattern. And then we can take the polylines of each face with face polylines from Weaverbird again. So those are now polylines, and we want to scale those polylines with different factors in order to have this diverse pattern in the openings. In order to do that, first we need center for the scaling for each polygon. We get that with the polygon center component, and we will need a list of values that we're going to remap here with some graph mapper, and then make it into a scale.
Radul, sorry, I
Yep.
don't know. Some people are just not really paying attention, so I have to just make some announcement again. So like I said in the beginning and a bit midway, and I'll say again, for mesh pipe and mesh surface, in the Dropbox, there is a plugin called Mesh Tools. Please install Mesh Tools. Okay, that's it. Yeah, Mesh Tools.
I'm going to bake some of the results for that. Okay. So are we waiting for people to catch up, or?
No, I think it's fine.
Fine.
So I was saying, even if you have mesh tool, when you open GH, you give the message error. I don't know. It's working for me. I have it open. I don't have any errors. I don't know.
They're having problems with the mesh tools.
Yeah, but I mean, I've installed it and I'm opening your files, and they're working fine. Yeah, I don't know. Also, there was someone saying that they can't get Lunchbox. I don't know, they're saying Lunchbox and Mesh Plus doesn't work for Mac, but they do work for Mac, so I'm not really sure what the issue is there. Maybe they're not listed as Mac on the forum, on the Rhino, but they definitely work for Mac. Fine. Not sure.
Okay, so can you continue from here?
Yeah, I think continue.
So we wanted to scale those faces with different factors, and for the values we can use, like for example, we can use different ways to get the list of factors, initial factors before remapping. Here, for example, I'm taking the center points. I'm deconstructing the coordinates. I'm using the Z coordinates of each center of the face. That's how the scaling factor is going to depend of the altitude of the face. So that's some principle. You can add, you can multiply here the value Z with the Y and then remap it and see what will be the result. The actual value, it's not that important, because here we first remap them and make them all between 0 and 1. By default, the remappers here in the target domain is between 0 and 1. And after running them through the graph mapper and the remap again with the new domain, here we want to have the target domain with some numbers between 0 and 1, because we're going to scale them and we want to make smaller polygons. So values here under 1 would make sense. And we're going to use those values to scale these polylines here. That's how we get this pattern. And the graph mapper here, so don't change that because it's connected to some heavy geometry after that. It's gonna take maybe a while to calculate, but the parameters here are, the graph mapper is controlling those values, and this domain here is controlling those, and that's how we get those different openings in the skin. So that was just for the scaling. Also, we want to actually move them in some direction from away from the surface here. So I'm going to take those same values here, and this time with a different domain between 0.7 and 0.04, for example, and then use it for amplitude for the vector that comes from each face normal. So each face here, it has its own normal. That means a vector pointing perpendicular to the face. And we're moving those scaled polygons with that direction and that new amplitude here in order to get some roughness in the skin. So once we have those polygons, we can use the three sets of polygons, the ones we've moved, the ones we scaled, and the initial ones. And we export the edges and we merge them, and then we make a mesh waft between each set of edges here. This component is turned off because it's one of the heavier one. You take a few seconds to calculate, maybe. So give it time. Yeah. So that will make a mesh waft between all sets of edges that we just created. And after that, we can join them and bake them. Obviously, that will take like 7 or 8 seconds as well, I think. So give it time. It's a lot of meshes, a lot of faces. So joining them and joining all the vertices, it's a heavy computational process. But it's better to have it all as one whole mesh if we're going to bake it and export it further for visualization or whatever. So we need a little bit patience with this. I hope it's going to be fine.
Radul, so they're having issues. I don't know why there's such an issue with the mesh tools because it's working. Like you can try to uninstall, restall, it's fine. Okay, so I'll explain again. MeshEdit and mesh tools do not have their own tab. The mesh components get put throughout Grasshopper's native tab. If it's not showing up, please make sure that you've unblocked the file once Radul is done there. Radul, if you can just show them where unblocking a GHA would be.
Yeah, sure. So when you go in the special folders, component folder here, that's where all the plugins are located. So do you say mesh tools?
Yeah.
So there's the mesh tools, just right click, properties.
And
sometimes you have a little unblock button here, you need to click unblock and then apply and okay.
Yeah. So if it's blocked, you need to unblock it, otherwise it won't work. It depends on your security settings for your computer and network. Sometimes when you download Grasshopper plugins, they become blocked because computers don't recognize that GHA so often, and then you just have to unblock it and it will work. If that doesn't work for you, I don't know what else to tell you. It seems working for a lot of people.
So maybe don't enable this Weaverbird join component because it took like almost 2 minutes here with me to compute. Maybe leave that for later. It's not that important. The point was it's better to have this list of meshes here joined together. I just wanted to show you the result. We have this pattern of different openings here, and we can easily experiment with that by changing the graph mapper or the values here that we're going to remap. Right now, if you can see, because we use the Z component of the centers, it changes vertically with the height of the geometry. If we use the X and Y, it's going to give some different results. So that was the skin with the openings, and if we want to close this skin, we're going to take this set of polygons here that we've moved after the scaling, and you want to make a mesh from each of those polygons. So the easiest ways to do that is take the control points of the polygons with discontinuity at the center point for each polygon, merge them into list of 5 points, and then make a de Wahl-Neu mesh from each set of five points here. And we can bake that, but we're not going to join it this time, but I'm going to just make it in a glass layer, let's say. Yeah, baking takes a little time too, I guess, because there are many faces. But you don't need to do that right now. Point was just to show how we close this outer skin. Okay, I'm going to delete those because it's some heavy geometry. Yeah, better. So that was one approach of making some pattern on the skin. Another way of doing it is like, again, we can, if we work with the triangulated mesh here, we can apply the mesh duo component from the Weaverbird, which will make hexagons and polygons with more angles than that we can basically apply the same logic as here. Again, take the center points, deconstruct to get some values for scaling and remapping them, and then after scaling we can move it. But this time for the vector we need to make additional vector, because those polygons right now, they're not faces from the mesh, they're just polygons, so they don't have normals. We need to find their own normals, let's say. So we are projecting the center of each polygon on the mesh here, and the 2 points that gives us a vector, and we use this vector for moving those scaled polygons in some direction in order to have this thickness of the skin. And after that, again, we just explode the 2 sets of polygons. We can merge them, make a loft between them, and the last step would be to close the caps or make a mesh from those polygons here. So we need to make a mesh from those. Again, like above, we take the control points, we add the center point for each polygon here, and we make the Wahl-Neu mesh from those points. After that, we can smooth a little bit with the Weaverbird loop subdivision, and then we can join it with the waft that we made between the edges. Okay, I'm gonna bake the result just to see what it's going to be. Yeah. So that gives us some other pattern that we can use for the skin. And then there are some different ways where you can experiment with patterns. Like, for example, there is the mesh plus. Just let me find it. The mesh plus tab. Okay. Sorry about that. Too many plugins. Oh yeah. So there's some types of different subdivisions here in the Mesh Plus tab where we can experiment with, and some other types of smoothing patterns. That's why it was important to have the mesh topology really neat, so we can further apply those algorithms. Those that we use here was just an example. That was the Catmull quark subdivision here, and the mesh duograph for hexagons, and so on. And if we another way of approaching this, that was for when we use the Weaverbird tool subdivision and work with triangulated mesh, but we can smooth this wall poly mesh here with the Catmull quark subdivision and work with quad faces. For example, and again offset once on the both sides here, so we can have those two meshes, the inner one and the outer one. Okay, and here we can work with some quad polylines. Again, use the same logic with graph mapper scaling. Here this time we can take the center, we will take the center point of each polygon, and we're going to multiply the x and y value, for example, and we're going to use these numbers for remapping and going through the graph mapper. This way the pattern is going to depend on the location of the face on the XY coordinate system. And that's pretty much the same algorithm that we used here before. So I'm not going to go really deep into it again. But again, we are remapping those values and we are scaling the polygons with those factors, moving them, and then we're just making loft between the sets of edges, and we are closing the caps again with the smoothened Deva mesh. So that would give us something like this. And okay, if we change the input here before remapping the numbers, let's say not multiplying x and y, but maybe y, x and z, it's going to change the pattern too. So we can have some different. Yeah, I'm rendering in this real time. That's kind of heavy. So maybe don't do that if you're not sure with your graphic card. And again, parameters here are the graph mapper type and the domain for the scaling factors. And that can give us some really nice skin view of the geometry. So that was a few ways of dealing with the mesh that we achieved in the previous chapter. Maybe I can now answer some questions about those few algorithms here. Let me just check. Okay. Do you have any clever methods of adjusting the topology to avoid the pattern bunching where the UVs tighten up together? Where the UVs tighten up together. Well, here we work with the topology of that mesh, and we cannot really change the topology of mesh of this point. But in the next example, we're going to work with some. We're not going to work with the mesh, but we're going to stick with the NURB surfaces, and then we're going to be able to tessellate it according to the curvature. So in this way, we hope to have to avoid this problem with with the UV tighten up together. So basically, you know, when once we have the topology of this mesh here, it's the pattern depends on it. That's why it was important in the previous chapter to have the topology in the way we like it. If we have the time to see the use of the M+ smoothing would be great. I have had issues in the past getting those to initiate. Okay, let's see some of the M+ smoothing. Okay, maybe let's try the, I don't know. Some of the smoothing algorithms there. The thing is that the smoothing with M+, it works with polylines, usually not with meshes. So we can try and take, okay, maybe this mesh here, yeah. So we'll take this mesh and we can take all the faces as polylines with Weaverbird face polylines. Okay.
Seems some people still don't have mesh loft. Not really sure why. I can't seem to reproduce that issue.
Okay, if you don't
if you
have a
just-
mesh loft, we have a
If you just
workaround.
yeah, I mean, but also if you just double click on the canvas and type mesh loft, it should come up if you have
Yeah,
mesh tools
don't.
installed.
Okay, so if you try to look for it, it's in the mesh tab in the primitive, but it's best just to look for it like this mesh loft. Just type mesh loft here. Same goes for mesh pipe. And
Yeah.
if you really cannot find the mesh loft, we can always do a normal loft here, but it will take more to calculate and visualize. That's why I'm trying to avoid it. Like we can easily and there are 3 edges here in each list. So make sure in the options here, okay, in WAF options, make it straight waft. So it will go straight through the 3 edges and not make some curve wafts. And you can then plug this here. And then we wait.
One person in comments said that they solved mesh loft problem by just reinstalling mesh tools and restarting Rhino, and it worked.
The thing is, sometimes the NURBS geometry it's easier to calculate. Sometimes the meshes are easier. It's not an actual rule, but okay. Sorry. Yeah. So as you see now, it's still the same. It just NURBS faces here, but it took like 33 seconds to calculate comparing to 2.8 for the mesh waft. That's what I do. And you can again just make this into a mesh by using the UV mesh from surface and just have this. Now, first, I think we need to deconstruct it because it's consisted from 2 faces each waft. Yeah, that's going to take a while too. And then make it a mesh, but it takes like much more time than the mesh waft. Yeah, so yeah, make sure you put the one into the UV before plugging the surface, so it's going to take less time to calculate. And it's harder to calculate and it's harder to visualize with the video drive as well. So if you have real issues with the mesh waft, just use the regular waft and then turn it into the mesh. But keep in mind it's going to take a while. Yeah. I hope that helps. I'm going to disable this. Yeah, as you can see, certainly it becomes a lot harder to manipulate the geometry. I'm just trying to delete this. Yeah, don't do that at home if you really don't need to. Okay, maybe look at some questions meanwhile. At many inputs of mesh, you have put relay function. Does that do anything to the input at the next step? No, the relays are just easier way to translate input from one component to another. It doesn't do anything. If you delete the relays, nothing's going to happen. They just disappear, but the whole algorithm recalculates. So keep in mind that when you are adding relays or deleting relays, it's actually recomputing everything after the relay. Okay, that takes a while now. Maybe I need to restart. Also, is there a way we can make planar faces with the panelization method we're using? No, if we want to have planar faces, we need to go through some planarization algorithms like Kangaroo or SL Sterling it has to, and not every mesh can be planarized. In this case, the geometry is really complex, so that will be not desirable. If we divide, like the more we divide the mesh into quads, the easier is to planarize each quad, but then the more quads we have, and in the same time it will take more time to planarize. So in this approach, we're not talking about planarization yet. If we want to keep them planarized, we just work with triangulated faces. Are we going to do an exercise from scratch? I think it's the best way to get through the whole topic, understanding every state of the algorithm, and then potentially come with some questions. Well, that was a question before, but we have a lot of things to cover, and I think I decided it would be best if we go through the logic of the components, because experience shows that if we start from scratch, we won't have time for much of the things I can show you by going through the definitions like this. Basically, it's more important to understand the logic of the methods, and then you can go through the components one by one when you have more time. Otherwise, we're going to lose a lot of time into putting the parameters on and looking for the next step. It will basically take like 10 times more time to go through all the stuff than now. I found a workaround. There's a plugin called Chromodoris that also has MeshWaft in it. Okay, there's a link in the questions tab for that workaround. I hope it works for those who can. Okay, that's done already. So I'm going to disable that because it's too. Yeah, so that was the part where we edit the meshes that we morphed. Now we can go to the third chapter, where we're going to work with surfaces and NURBS geometry and surfaces. And we're going to do that by going through some sub-D geometry before that. Basically, the idea here, some parts of the idea are the same. We make this whole poly mesh from the periodic surfaces, and then we morph them into some twisted boxes. Some twisted boxes that we design. The mesh here, I'm using this second example from the first chapter, but at the end, when you get to the, where was it? Yeah. So when you get to the NURBS curve, I just make a low poly mesh from it with subdivisions of the UV and value one by one, and then joining them and welding them. And that's the geometry that I'm going to use here in the third chapter for morphing into twisted boxes. So this one we already have. The second part is creating some twisted boxes, and that's really up to you. How will be the silhouette of your design and the overall shape. You have a lot of freedom and a lot of different ways to create those twisted boxes. In this particular example, I'm going to be using two sets of polyline curves. And we're going to make twisted boxes between the segments of each curve, of each curve. Doing it this way, we have the opportunity to further change that shape, and that will get us flexibility of the general shape and the silhouette of the design. So you can change those shapes. It would be nice if you keep them in the same planes, because that's how the design is going to work later. But in any other regard, you can manipulate and change the orientation of those curves as you like, those polylines. So once you have the two sets of polylines, we need to find a way to make twisted boxes between them. So for that, we're going to use twisted boxes consecutive meshes. So, I mean, that means we're going to make layers of meshes between the two sets of curves, and we're going to use the faces of those meshes for the twisted boxes. So first we make a loft between the two sets of curves. We deconstruct the two lofts, and from the faces we make UV meshes with U and V value 1. So we just have those two meshes constructed from each has two faces, and then we can twin the two meshes in order to have this third one, and that the twin factor is going to be a parameter for the location of this middle layer for the twisted boxes. So that will change the topology as well later. Right now I'm going just to keep it at 0.5 because I want to have this middle layer just in the middle between the two controlling sets of curves. Once we have those three meshes, we just merge them in one list of meshes in the correct order, 1, 2, 3, and then we use the twisted boxes through meshes component. Here we put the three meshes, and for the W parameter, we need just a range from 0 to 1, because that means the number of divisions between each layer of meshes. So if I increase that, it's going to start dividing that. But for right now, for now, we're going to keep this at once and have only one division between the separate layers. By the way, we're going to make this design right now. That's the setup for this geometry. After we have those list of twisted boxes, next step is to morph the initial mesh into those twisted boxes. In order to do that, we're going to need a bounding box for the geometry, and you can experiment with by mirroring the initial mesh in different directions. That's going to give you a different topology, since this periodic surface looks kind of different when it sticks together in the different directions. So for example, if I'm just going to copy all of this just to show you.
They're asking if you can put the bifocals on.
Oh, sorry. Thank you. So a parameter here would be the orientation of the mesh, and the plane for the bounding box of it. So So if we change the orientation of the bounding box reference to the twisted box morphing, like right now it's in the XY plane, but if we change it with the YZ plane, it's really going to make some different output here. And same goes right now. I mirrored once the mesh here, and then rotated it in some plane. If we change the mirroring planes or the rotation planes, again, it's going to have some different topologies here. Maybe if I'm going to smooth that to show you. Yeah, before smoothing, we need to join and weld and unify the normals here. And after that, we can now smooth the whole topology. Yeah, so anyone like this. So as we can see, there's a lot of versatility in this simple algorithm. Only by changing the orientation of the initial geometry and the plane for the bounding box, you can get really different shapes that you can work with later. So that's why there are those mirror and rotate and XY, XZ, and YZ planes here. So you can experiment with different orientations for the morphing of the meshes here. And once we morph the mesh, as I said, we need to join weld the vertices. And for now, we're going to need to keep this wall poly. We're going to make this into sub-D geometry, and then into NURBS geometry, and work with NURBS geometries this time, not with meshes. In order to do that, we simply need to bake this first. After the unified mesh, we can bake it, and before turning it into NURBS geometry, I'm going to put those points here in the front on the ground, because that's where the whole thing is going to step. So I'm just going to select those few points here that are in the air, but they're supposed to be on the ground, and going to move them vertically, right, like this. And you can change the geometry here as well before turning it into sub-D. You can change it after that too, but it's easier when to look at the low poly mesh before do that. Once you have that, right, the Rhino 6 has this turn to sub-D command, and it's going to ask if you want to delete the input, and I'm going to do no for now, and that will change the geometry into sub-D geometry. So I have this in Rhino 6 as well, although the Rhino 7 has a whole new world with sub-D geometry as well, but we're going to stick with just those few simple commands here from Rhino 6 for now.
Hey, Radul.
Yep.
I just realized something. I think people that are having only mesh pipe and sweep, but not loft, I think they may have downloaded an old version. Actually, the old version of Mesh Tools is the only one publicly available.
Mm-hmm.
So if you've downloaded it from the internet, you have the old version. So make sure to use the version that we've put in the Dropbox. That's the version with all of the mesh tools. That isn't anymore, unfortunately, online. Okay, you can continue.
Okay, I didn't realize we are so underground with those plugins this time. But yeah, so the command here was to turn this mesh into sub-D was just a simple 2 sub-D. That's it, 2 sub-D, and it turns the mesh into sub-D that you can, if you turn on the control points with F10 here, you can further change as you like as well. But before turning it into sub-D, I'm going to offset this initial mesh into 2 directions in order to create an inner and outer shell for the design. So this mesh here that I edited and put those points here on the ground, I'm going to input it here in Grasshopper again, set one mesh, and you can internalize that in order to be able to delete this. And then we offset this mesh into 2 directions. So make sure you have the both sides on true and make solid on false. And you have a parameter here for the distance between 2 meshes. And then we have those 2 meshes that are going to be the inner part and the outer part of the design. And now I'm going to bake those 2 and just turn them into sub-D geometry. So I'm going to select both to sub-D. I'm going to delete the output this time. And then I'll have these sub-D geometries for my inner and outer part. And because we are still working with Rhino 6 here and Grasshopper, we need to make those into NURBS geometry in order to put them in Grasshopper. So in order to make the sub-D geometry into NURBS, just type 2 NURBS. And we're going to delete the input objects again. And now they're polysurfaces, as you can see. So now we can upload those here into those two breps, the inner surface, the outer surface, and the inner surface that we're going to be working from now on. Those are basically here the white part in the inside and the black part on the outside in the design. So those are now breps, and they're composed from quad surfaces, untrimmed surfaces, and from now on we're going to work with NURBS geometry this time, not with meshes. So the first part would be again to make the connection between the 2 inner and outer part, because right now they are just not connected, they're parallel. In order to do that, we're taking the edges from the breps, the 2 sets of breps, and we are taking just the naked edges, joining them into 2 sets of curves. And in order to be sure that we're going to match each pair of curves, first we're going to sort the indexes of those curves depending on their z coordinate. So I'm just making a bounding box for each curve. I'm getting the center point for each bounding box, and I'm sorting this list of curves according to those z coordinates for their center points. That's how I'm going to make sure that the 2 lists of curves are going to match with their neighboring curve. Also, another thing we need to do is align their seams, because otherwise, as you can see here, their starting points do not match. So after using the align curves and seam with some guiding points, the starting points of the sets of curves are going to match, and then thus we can make a waft between each pair of curves. And if we need, after that, we can always, of course, make it into UV mesh with a certain value for U and V. So I'm going to bake that just to have a visual of it. So that's the part that connects the inner and the outer surface of the design. Next part. So you can, if you look at the whole definitions, there are different groups of components that they do different parts of the design, like the opening, the modeling of the openings, the panelization, and the railings and the slabs of the design. So first, we're going to start with doing those openings here in the design. As you can see, I've decided to treat the surfaces differently according to the orientation of each surface. Like, for example, it doesn't make sense to put some openings on the floor, on the ground. We want to make some openings only on the surfaces that are facing upwards, and treat the surfaces that are facing downwards in a different way. Here, they're just panelized. So first, we need to separate the two kinds of surfaces: the ones that are facing upwards, and those that are facing downwards. In order to do so, we're taking the faces here from the deconstructed BREP, and those are the untrimmed surfaces that construct the whole geometry. And we are evaluating those surfaces with the evaluate surface, and we are taking the normals of each surface. That means that's a vector, and if this vector is pointing upwards, that z value should be positive after deconstructing that vector. And if the surface is pointing downwards, that z value should be negative. So if I compare that z value of their normals with 0, that will give me a pattern where I can split those surfaces into those facing downwards and those facing upwards. Another thing is it doesn't actually make sense to put openings on those first few surfaces here at the bottom. So I'm going to add another logic to it. Like, I'm going to compare the z coordinate for the center of each surface here, and I'm going to put a certain value, like, let's say 5.5 meters. That will give me a pattern to divide the list of surfaces into two lists: the one that is above 5 meters and the one that is under 5 meters. And with this pattern here, I will just list the indexes of those surfaces that are under this value, and I'm going to get the indexes of those surfaces that I already found are facing upwards. And when I do a set difference between the two sets of indexes, that will give me a set of indexes for the surfaces that I really want. Those are going to be the surfaces that are facing upwards, and they're above this value here. So that gives me a list of indexes, and I can easily use it to go and accordingly list this group of surfaces into two lists. So that gives me the two lists that I'm going to work with. I'm going to put the openings here on that list of surfaces facing upwards, and I'm going to treat those differently later. So let's continue with making some openings here on those surfaces.
Hey, Radul,
Yep.
before you go on, do you want to take maybe a few minutes break or?
Yeah, that'll be good, I guess.
Yeah. Okay, so what, we can take like 10 minutes break or so.
10 minutes, yeah, sure.
Okay, so
Okay, guys.
just seemed like a good point to stop for a minute. So.
Yeah.
Okay, everyone. So we'll take a 10-minute break, and yeah, in the meantime, feel free to play around a bit with the definitions or grab a coffee. Just come back in 10 minutes.
Okay, see you in a bit, guys. Okay, I hope you guys rested a bit and you're ready to continue. Meanwhile, I can look at some questions here. Is there a strategy to use overlapping stripes instead of panelizations? This to have the flat stripes that you can bend into the following topology of the surface. To be honest, that's a good idea, but I'm not actually sure. Not every topology can be unbended with flat stripes. That depends on the curvature there. And the same question is this a kind of resulting meshes easy to unroll on stripes with quad mesh? No, it's not easier to unroll those quad meshes. The unrolling depends on the curvature of the initial surface. Would you be able to quickly explain again how the definition is differentiating surfaces facing upwards and surface facing downwards when you get back? Okay, I'll go through this part again. So here we have the list of surfaces. And first we are evaluating those surfaces in their middle point here. That gives us a normal, a vector for each surface pointing in some direction. Okay, I can visualize this vector, maybe. Sorry. So as you can see, each surface has a vector pointing in some direction. And when we deconstruct this vector to its x, y, and z coordinates, if the vector is pointing upwards, that's going to give a positive value for the z. And if it's pointing downwards, that gives a negative value for z. So if you compare that z value of the vector component of the vector with 0, that will give us a pattern in which we can differentiate the ones that are pointing upwards and downwards. I hope that makes sense. For some reason, still problem with Pufferfish. Can't help that right now. On the provided definition, the inner and outer BREP is already populated. Where does it come from? In the previous step, we baked the mesh. How does the mesh turn into a BREP? Okay, I'll repeat that again as well. Like when we have this morphed mesh here, we baked it. We adjusted the points of the mesh a little bit here, and then we put it back in Grasshopper. We offset it here with some value, and then we bake those two inner and outer meshes. After that, we select the two meshes that we created. Okay, and just that's a Rhino command here. Type 2 sub d, and that makes them into a sub d geometry, as you can see. And after that, we type again in Rhino 2 NURBS, and that makes them into poly surfaces. And then we can just input those two surfaces here in the BREP container for the outer surface and for inner surface. So bake the mesh, the wall poly mesh, make it sub D, 2 sub D, make it NURBS, 2 NURBS, and then import it again in Grasshopper. After that, we differentiate the surfaces facing upwards and facing downwards, so we can continue working on them in the two separate ways. So first, we're gonna do some openings here on those surfaces. For that part, we're going to use Lunchbox hexagon cells division with some values here. You can try different UV values and different parameter for the transformation from the angles of the hexagons. Maybe it's going to look nice with smaller count and larger openings. It's totally up to you. After that, from those cells, we need to work only with the hexagon cells. So that means we need to get rid of those half cells here that are on the boundary of each surface. So in order to do that, we're going to take the control points of each cell and you're going to take the list length of each list here. That means the number of control points for each polygon. And we're going to compare that with 6. That means that's going to give us a pattern that we can dispatch the list of cells from the hexagon cell division into those cells that are hexagons and those cells that are not. And we're going to continue working only with the hexagon cells here. So after that, the next steps are pretty much the same as the previous chapter. We're going to scale those polygons. We're going to move them a little bit. We're going to make some wafts between the new edges in order to produce those openings here. So first, we're going to find the center for each polygon with the polygon center. And we're going to use this center for center of scaling. And first, you're going to scale them all with the same factor in order to make the distances between the openings. Then we need to project those polygons into these surfaces here. So don't forget to watch for your data management. Here we need to graph the surface in the beginning. And here we need to project those polygons into those surfaces. And the direction for the projecting them, we need to take from taking the center of each polygon cell here, projecting that center into the surface here. That's the surfaces, and that gives us vector from the 2 points, the center of the polygon and the projected point. That gives us a vector. The reason for this is because those polygon cells are not neither planar, and their center point doesn't necessarily belong to the surface where the corners are. So the center of the polygon is projected on the surface here, and those 2 points give us direction for projecting those polygons into these surfaces. After doing that, now those curves here, they all belong to the surfaces, and we can use them to split the surface here. So I've turned off this one because, again, a heavy computational component is going to take a few seconds to compute. Here we input the surfaces that we are working with, the ones that are facing upwards. And for cutters here, sorry about that. Okay, 10 seconds. And for cutters, we use those curves that we projected on the same surfaces. That's how we first make sure that the curves belong to the surfaces, and then we use those curves to trim the surfaces. Before that, we need to trim the tree because this component here grafts the list a little bit. We need to make sure data management is good. So for each surface here, we can go to trim it with 25 polygons each. So that splits the surfaces into 2 parts. This outer part there is one connected trim surface, and those 25 trim surfaces that are the actual openings. And so we need to split the list of surfaces here. It's going to be 26 from each into two lists in order to get this part and those parts. And we do that by adding a simple rule. We first sort this list of surfaces according by their area, and obviously this outer surface here is the one with the biggest area. So after I sort those surfaces by their area and I split the list after the first item, I'm going to have two lists with this outer surface and those openings here. So from here we work with those patches. We're going to make the openings from them. In order to do that, we first evaluate them in their center point by taking the center point, projecting it into each surface here, and using the UV coordinates for each point in the evaluate surface component. And we need that to get those frames. Okay, I'll make the preview size smaller. Yeah. Yeah. So that gives us the point, the center point for each surface, and a vector facing upwards from the surface. I'm going to use this vector to move a little bit the polygons in order to have these parts here, like the thickness of the openings. And we're gonna make this different value according to the opening size. So for the scaling factor, we're going to repeat that concept from the previous chapter. We're going to take the distance from the center of each polygon here. That's the point P. And you're going to measure the distance this time to the naked boundary here. So for scaling factors, the scaling factors are going to depend on the distance from for each of those polygons to those boundaries here. So the further away from the boundary, the bigger the scaling factor, or the opposite, something like that. That's why I'm using Pu component, and then we're finding the closest point for each point to this edge here. Those are the naked edges from the BREP. And those distances I'm remapping, and I'm putting through this graph mapper and remapping again with the center with certain target domain. Again, it needs to be between 0 and 1 because we're going to use those as scaling factors for each opening. So I'm scaling those openings with those factors, and here I'm moving them away from there by using for vector here the normal that I found on each surface, and for amplitudes I'm using the same graph mapper, but I'm remapping the numbers with different values here. So first I'm scaling, then I'm moving. It's the same like we did in the previous chapter. And then I take the wires from those new sets of polygons, and after merging them into one list, we do a loft here in order to get that. So that gives us this nice pattern with different heights and different scale factors. And after we merge those with this surface here that we dispatched earlier, that gives us a part of the upper shell of the design. So I'm going to merge those here. I'm going to group them, and then now I'm going to bake that into outer surface layer, just to know that I'm done with it. Another thing, I need to fill those openings here now. I'm doing that by using these sets of surfaces before getting their wires and making their WOFs. Those are patches, and I can just group them and bake them into the glass layer. Okay. Glass layer is kind of invisible. Maybe I'm just going to make it less transparent. I don't know. Yeah, just for now to visualize it. Yeah, so that's one part of it. Now we need to do the same thing with the part of the surfaces that correspond to this, but in the inner shell of the design. Like after we have those indexes here, which we use to dispatch the surfaces into upwards and downwards, we can use those same indices to dispatch the inner faces. Pretty much the logic that we do with the components in black, we need to do with the components in white, and that's going to be the inner part of the design, basically. So that's the inner surface here. Again, we deconstruct the faces. Again, we take the wires. Okay, just a second here to remember. Yeah. Sorry about that. So here we need to make first this panelization. Let me just show you here on the picture. Like we need to separate the panels from each other, and we need to have those like edges from the surfaces, because it shows the tectonics of the whole geometry, in my opinion. So that's why after taking those inner faces here, first I'm taking the wires from each surface, that means the outer edge, and joining them into polylines, and then we can offset those polylines. That will take a while too. We're going to offset the polylines here on the surface, so each polyline is going to be offsetted in the same surface that it belongs. So we will have two sets of lines of curves. The thing is, the direction of offsetting depends on the direction of each polyline curve here. So that's why this component offset on surface let me just show you first what we want to achieve with all of this, and then I'll explain. So I'm taking each of those surfaces and I want to offset the edges here inwards, so I can trim it then and have this contour between the surfaces. So here we use offset on surface component. It takes a curve and a surface that it belongs to, and it offsets the curves in a way that the new curve belongs to the surface. The thing is that the direction of offsetting depends on the direction of this curve here. So it goes for red because some of the curves are offsetting inwards and some of the curves are offsetting outwards, but the surface it's finite. So if the curves here are offsetted outwards, it doesn't have enough surface. It doesn't know where to go. So it just offset some of them. That's why I'm doing the same here, but a negative value for the offset for those curves that are unable to offset the first time. And then I'm merging the two lists here. So that will give me all the curves offsetted inwards in the right direction. And I'm going to use those curves to split those surfaces. And again, that splits each surface into two surfaces, that inner panel and that outer edge. So after I sort those faces here according their area, that gives me these inner panels and those outer edges that we're going to visualize as those lines here, those stripes here. So pretty much it's like I offsetted those surfaces with a certain value inwards, not changing anything else. And then from this list, I'm using the indexes here that I did earlier in order to separate those again into those that are facing upwards and those that are facing downwards. So with the list of surfaces that are facing upwards, I need to put the openings that I made here on them as well. That's why I'm taking this list of surfaces facing out upwards, and they belong to the inner part of the design, inner surface, and I'm projecting the openings that I did earlier on those surfaces here. And in order to do that, again, I need to take those openings and join them just in case, because sometimes the geometry crashes a little bit, and then find the vector for the projecting, which comes from the polygon center point and a point projected on the surface here that I wanted to cut. So that gives me the vector, and when I project those openings onto this surface, I can then again trim the tree in order to get the data in the right order, and then use split surface to cut the same openings from the outer surface into the inner surface. Just give it a second. Yeah. So now those surfaces are split. And again, if I sort them according to their area here, and I list the biggest one, that's the inner surface that I want. So I can merge that with, I can bake that into inner surface, and it's going to give me this. And the last part is I need to connect the opening here with this inner surface. So I'm taking those openings from the outer surface and I'm merging them in the same list with the projected polygons. Close them just in case if the geometry is broken. We need to align their seams, because in order to make the loft, they need to have aligned seams first, the starting seams, and then just make a loft between the two pairs. And now I can bake that into the inner surface layer as well. And that causes the thickness of the geometry, and still having the holes. So far so good. We have the openings on the outer and the inner surface. The next part we decided that we're going to treat the surfaces pointing upwards and downwards different parts. So now we made the openings on the surfaces pointing outwards, and for the rest we're going to use this tessellation. It's called surface quad tree by curvature, and a C script. It's a C script component that I'm not sure, I forgot where I got it from. Maybe I need to credit someone, but I really couldn't find the source for this component. It's not in the Grasshopper native components, but I found it somewhere. And basically takes that list of surfaces that are pointing downwards, and it tessellates them according to their curvature. So in this way, if the surface is more curved in places, it tessellates more, and the opposite. That gives us this pattern. So after we have this, we need to panelize it. Basically, have it made, have the edges shown here, as we did with the bigger panels. And the logic behind it, it's again the same. We need to take their wires, join them, offset them on surface. That's going to take a while as well too. Basically, the components that are surface split or solid trim or offset surface, they're the heaviest. So if you're trying to play with some of the parameters in this definition, make sure you disable the components that are the heavy for computation. This takes like 14 seconds to compute because it's heavy geometry. If you have this useful tool, MetaHopper, you can launch the bottleneck navigator, and it shows you the components, the most computational heavy components in the right order. So as you can see, those offset takes like 15 seconds. It's like 20% of the whole definition. So if you want to play with the parameters, make sure you disable some of the components that are really heavy and make the definition heavier. Otherwise, you're going to have some tough time, and maybe Rhino is going to crash. But so we did that before. Now we did it again. We offset those polygons on those surfaces. This time they're all in the same direction, so we don't need to do this in two directions. One is okay. And we use those new polygons to split those surfaces again here. So split surface, enable this. Give it a second. Yeah, so we are splitting the surface here, and again we are sorting. This time each surface is split into those quad panels and those so-called edges or thick lines between those that's one surface, the thick lines, and the other group of surfaces are those quad surfaces. And we need to separate them into two different lists. So we need to think of a rule how to differentiate between them. And it's obvious that this surface that represents all the edges in the inside has the largest length. Like if you take the contour of it, it's going to have the largest length. So here I'm taking the wires of the surfaces and I'm measuring their length, and I'm sorting the list according to their length. And obviously the longest, the one with the biggest perimeter, is going to be this surface here, which represents this, like the edges of the panels. So that goes for one layer, and we're going to offset the other set of surfaces here, which are pretty much the panels. We're going to offset them a little bit just to make it look like a panel and give it some thickness. So that's why the offset surface here, again, computationally heavy. So make sure you disable that after if you want to change something. Yeah, that probably is the heaviest component in the definition because there are a lot of surfaces to be offset. It takes like 30 seconds. Let me see if there are some new questions meanwhile. Yeah, so we offset them, and those are basically the inner panels of the design. So I can group them and bake those into inner surface layer like that. And this geometry here, the edges, yeah, we can bake it. Okay. Several joints. Yeah, I can bake this. I'm gonna bake it into metal layer, just to know that I'm done with it. Yeah, so we achieved this nice bump and separation between the panels. What is next? Okay. So the whole logic here, we can do it again the same way, but on the surfaces that are on the outer surface and are facing downward. So those are the ones that we are missing, and it's the same logic here. We first tessellate it using this algorithm here that tessellates according to the curvature. Then we take the wires, we join them, we offset them on the surface, and then we trim the surface, we extrude the surface, and that's it. So offset the curves, split the surface with those curves. Okay, that's done. And we take the wires, we sort the surfaces according their perimeter, and then we split the list, and this goes into one layer. And the other we offset. Okay, we offset the surface in order to give some thickness to the panels, to the different panels. By the way, if you want to be fancy, you can always input here in for the distance offset some list of values and have some different thicknesses according to some rule again. And we can bake this into the outer surface layer. Okay. Yeah. So we have the inner and the outer panels right now. I feel like I'm missing something. I forgot maybe to split those parts here where the openings are. It was maybe because I did not actually let me check why. Maybe I forgot something. Yeah. So it's okay, we can leave that. We can leave it like this, but we can apply the same logic for cutting those that upper surfaces, and the whole point is for having those edges visible for the upper surfaces as well, right here. Maybe it looks okay like this too. Kind of like it. Okay. So let's see what's next. We did the panelization here. We did the openings. What is left is to model the railings here and maybe put some slabs in order to make it more architectural. Also, we haven't, yeah, I need to bake this, the connection between the inner and the outer parts, which was maybe here. Yeah. Okay, so I forgot to, it's only in the beginning here. I forgot to offset those. I'm just going to hide it, everything for a minute. In the beginning here, where we have the initial surfaces between, before making panels and openings in them, we need to first offset those curves into those surfaces like we did with the inner ones. And thus we make all those contours between the large panels as well that we are missing right now. So here we're taking the wires of the surfaces, joining them, offsetting them 2 times because they're maybe in some different directions. So not all of them are going to be offsetted with the positive value. Some of them needs to be offsetted with negative value here. And then, just a second. Yeah, it's going to recalculate what the algorithm after that. So if your computer takes time, just give it a minute or two, and it's going to be fine. Don't crash it. Let me check. Is there any new questions? Not so far. And I enable the second one. And again, I already said that, but I'm going to say it again since we're going to wait a bit for calculating anyways. This goes red because when we offset those curves onto those surfaces, some of them are offsetted outwards from the surface, and some of them are offsetted inwards of the surface because that depends on the direction of the curve. And those who are offsetted outwards, they don't have enough surface to be offset on, so they don't calculate. This calculates only those who are offsetted inwards, and for the other half of it just gives a null. So that's why we are offsetting the same set of curves, but with negative values. That's how we make sure we have the full list of curves here in the merge, offsetted inwards onto each surface. And then we use them to trim the surface and achieve the edges between the panels. Almost there. Will we get the Grasshopper file at the end of the class? Well, yeah, but you already have it. Like I can set it again if, but I'm not doing many changes to it. Okay, so it's done. Yeah, so we offset all the surfaces, we split with the curves here, we sort the new surfaces by area, and then we have those that we later dispatch and put the openings here, and this here are just the edges between the panels. So I'm going to delete this group here and this here. Yeah, and I'm going to bake it again at the end here. So that was outer surface, because this time it's separated on different panels. That was the glass, I think. Yeah, the glass I could have just let as it is before, and here, what was that? Yeah, that's the inner surface. And now I can bake this into the edges layer that I have called metal. Yeah. Yeah, so now it looks as intended. We have those big panels with openings, and we have those smaller panels that are tessellated according to the curvature, and we have it the same on the outer part and the inner part. So what we are missing is the connection between the outer and the inner part. I think it was here, yeah, like I think I explained that. We take the naked edges from this initial BREP from the two layers, we join them, we sort them according to their altitude, we align the seams, and we make walls between them, and I can bake this now into this layer too. Let's see. Yeah, as intended. So what it's left is to close the the design with some slabs and some railing. This is made here in that part, railing modeling and slabs modeling. In order to do that, okay, so we're going to apply first the railing, and it needs to be on those naked curves here. So this component comes from getting all the naked edges of the inner surface here. So naked, the wrap edges, we take only the naked ones. That's from the wrap here, not the deconstructed wrap, but the whole wrap where the surfaces are still joined together. That's how we get, where was it? Yeah, we get only just those outer curves, which are naked edges for the wrap. We join them, and if you can see now, we don't need to put railings everywhere on those. We need it only here, here, and here. So that makes sense here, here, and here. That corresponds to this curve here, and this curve here. So we just need to, from this list of curves, we need to find those just 3. And I do that by listing them and making a gene pool with 3 sliders. It's kind of lame doing that, but it saves time, so it's okay. Just put the list and change those, make the gene pool with only integers, and change them until you find the ones that you actually need. So those are the 3 edges that we want to put the railing on. So next up, how are we going to do that? We need to shatter those curves in some height, and then we're going to make a loft between the bottom curve and some horizontal curve that corresponds to it. So first we take that, we make the bounding boxes of those curves, and we only want to take those bottom planes, which is, that's why we deconstruct the wrap and take just, that's the number 4 of those faces always for some reason. So that's the bottom plane for each curve. So now if I move this, like I put XY plane here on each, or you can just actually make it with the face itself. It's going to be treated as XY plane as well, but I put an XY plane in the middle of it, and then I move it with some height that will correspond to the height of the railing, because I'm going to use this plane to intersect those curves with that plane. Like if I increase this, that's going to go up. If I decrease it, going down. That intersects the curves with those 3 planes. And then we use this parameter of intersection for shattering the curve. And then we just need those bottom curves, the bottom part of the curve. And it's not always the first one. So first we need to sort this list of curves according to a Z value for a point on that curve. So I'm just, each curve now here is separated into 2 pieces. And after I take a middle line for those 2 pieces, I sort them according to their Z value. And then I can just list the first one, which is going to be the bottom curve. So that's the bottom curve. And I can project this bottom curve into this plane that I made, that I shattered the curve with. And after merging and making loft between the 2 curves, and just give it some thickness with surface offset, not to make it flat, that's going to be the actual railing here. So I'm just going to bake that and show everything. Yeah. So this parameter just controls the height of the railing. And that's pretty much it. This Gimpo controls in which part of it we want to put the railing on. And that's it. That's pretty simple. And the last part is closing some of the openings here, making sort of a slab. In this design, I like to represent it as some glass floor with some subconstruction on it. So we're gonna do that by, I'm gonna hide that again. I'm going to delete this. Yeah, so after I take those bottom planes for this for the layering, that's the basically the levels that we are making. We can intersect the BREP, so the whole geometry, as when it's a whole BREP, not the deconstructed BREP, but the whole BREP. We can intersect it with those planes here, and that's going to give us the contours of the slabs that we need, basically. They'll intersect the BREP with the horizontal XY plane and gives us those strange contours for the slabs. And in order to finish them, right now they're kind of weird shape. It will be better, and it's curved, right? This is curved because it's intersection between an XY plane and a NURB surface, and I would like to make them into polylines because you'll be easier to work with later. Like, it still has pretty much the same, but it's kind of a low resolution of those curves. So I'm using the curve to polyline component here. I'm going to offset it inwards a little bit, not to intersect with the walls too much later. Maybe I need to show everything in order to make more sense. Maybe that's better. Yeah, so those are the curves. And if I make a boundary from those and just extrude it a little bit, I can say that that's some glass flooring that I'm making there. So I'm just going to bake that into slabs layer. And where it's left, I want to make some subconstruction, not to leave it like a flat, thin slab. I'm going to make something that represents structure underneath. So I'm going to take this contour. I'm going to offset it again a little bit, just in case. And because it's somehow a weird shape, it's not like we can apply some regular pattern on it. Like, we cannot divide it to new V direction because it's a trimmed surface. So I've decided we can divide it with a Voronoi pattern. It's kind of easy, and we're going to see how it looks visually. The way we do that is by populating those surfaces here that represent the glass with some random points. The number of points here is going to be a parameter, and we make some Voronoi cells out of those points. And next, we just trim those Voronois with this initial region here, and we take only the curves that are inside the regions. So we get this pattern into those regions, and what is left is just we merge it with the outer contour, and then we offset it on the both sides here. I'm going to put a true toggle here just to make sense. Yeah, so offset it on the both sides, and then make boundary between them, and then just extrude them, and that will represent some structure. Extrude them with the negative Z direction, and that will represent some structure under the glass flooring. So I'm just gonna bake that here. Yeah. Okay, let's see what we got now. If I unhide everything. Yeah. So that's enough for this design. Maybe quickly I will go through again through the whole logic on it. You can see it in the visualizations in the webinar. Here I just use some other pattern for the force under structure, but it's pretty much that. And if I can recap, we started with this wall poly mesh made from periodic surface. We morphed it into twisted boxes that are controlled by two sets of control curves. They do a list of twisted boxes here, and we morph that wall poly mesh into those twisted boxes. We join, we weld, we unify normals, and then we bake it. We transform it a little bit. We offset it for the inner and outer surface, then make it to sub-D geometry, and then make it to NURBS geometry, and that's what we inputted here in those BREP components, the two sets of surface, the two BREPs that represent the outer surface and the inner surface. And then first we treat those surfaces in two ways, one for those that point upwards and different for those who point downwards. We make hexagonal openings in the surfaces that point outwards, and we panelize the surfaces that point inwards according to their curvature. Then we make the contact edges between them, and the whole thing we did again with the same logic and parameters for the inner surface. Then we connected the two parts, and we modeled the glass rating and the glass slabs. So everything is here. I know it's a lot. When you have more time, you can go through this, the recording again, and follow the components one by one. But I think it's a really good exercise for both for beginner and advanced people in Grasshopper. And I think here you can find a lot of logic groups of components that you can apply on different scenarios and different designs. I've tried to show some different geometry, some different approaches for panelization and tessellation. Of course, the design is really subjective. I hope you guys manage to play with the definition and come up with something by yourself. And maybe right now I can answer a few questions about this chapter before I go to the last 4 chapters. So maybe a few minutes for questions if you want me to explain something again, to repeat it. How can I make transitions of color at the glass? You mean here in the visualization, I guess? Well, that's rendered in a different software. That's in Keyshot. So if you're using it, that was some layered optics material, I think, which really reflects different colors of light depending on the angle that you're facing, and some really nice effect. The offset surface not working at the quad panelization. Well, it's red, but it's actually working. If that's, or maybe the quad panelization, where was it? Yeah. Okay, let me just, it's in this. If it's not working, maybe try not to use the opposite value for distance. Like if it's not working with positive value, try with negative value. Because for some reason, sometimes actually the direction of offset changes with every new definition opening. So that goes for changing for offset of curves and stuff like that. So maybe if it's not working here with the negative value, try plugging in the positive value. Sometimes that's a problem. At the end of the definition, surface morphing before offset mesh, my mesh component has orange warning. In the end of the definition, surface morphing before offset mesh. Yeah, it's because you need to bake this mesh here, the ones you morph into the twisted boxes. You need to make it to transform it a little bit just to put those points on the ground, and you need to load it here in this container. That's reference to Rhino geometry, but I internalize it, so maybe we have nothing here. Can you do a recap of what we should bake to get to the final form? Sure. So like I'm just going to do it again. So first we made the connection between the two inner and outer parts. So that's basically the thickness of the whole composition. So bake this. Then we did the outer surface openings which are facing upwards. Here at the end, that's one group. We bake this in the outer surface. Then that's the glass, basically the fillings of the openings. So bake this in glass. Then if you go down, we did the same with the inner surface. So you punch those openings in the inner surface. So bake this in inner surface. And this waft here is the connection between the inner surface and the openings. So this goes in layer inner surface as well. Then what do we have here? Here I've merged all the contour edges of the panels. So this merged geometry comes from the smaller panels and the inner and the outer smaller panels. So this goes to layer metal. Then we went through the panelization, I think. Yeah, so that's if it's in white, it's in the inner surface. So that goes into inner surface. Those are the panels that are offsetted. And that's the same, but on the outer surface. So it's in the outer surface layer. Bake the panels. Yeah, what I'm missing those edges here, which were somewhere. I think it was this one. Yeah. So this needs to go into the metal layer again. Yeah. Just a second. Yeah, so what it's left is the railings and the slabs. So the railing was here at the end in purple. You bake this in glass. That's the floor subconstruction. We can bake it in dark metal. And the glass slabs. Yeah. So what I want to recap from this example is that working with NURBS and then accordingly sub-D or relevant breps, it's really much more accurate as a geometry. Like we can have a really precise geometry everywhere. It's great for fabrication. The negative side of it is some components takes more time for computation, like the trimming and the splitting and the offsetting surfaces, but that's quite normal. And those are the difference between working with meshes and working with NURBS geometry. You can decide for yourself which result do you like better. So we have around 1 hour. We can go through the 4th chapter here, which is an example for this design. Again, there are different parts of the definition that do the different things of it. Not sure if you have the time to go through all of it, so I maybe go faster through some of the parts because it's a lot, basically. So let's not waste more time. Yeah, I'm going to move that a little bit and hide it. Yeah, so open the next file that says number 3 cell. Here we use again the Millipede plugin. And this time we're not going to use the refined mesh, and we're not going to make it into NURBS. We're going to use it as it is from the Millipede output, but we're going to keep it really low poly, so we can the topology stays nice, and we can further adjust it according to our desire. So we are using the Schwarzschild equation for the mesh. You can copy this whole setup here from the first file. The only difference, you can keep this in close to 0. The difference is that we're going to lower the resolution here and the minimum, which is 4. That's why it's really a low poly mesh here. And the thing is that the output from Millipede sometimes have some really small faces and naked edges that you cannot actually see here, but they're here. So that's why first I'm going to clean this mesh a little bit and just need to, I'm taking the naked polylines of the mesh and I'm measuring the area of those faces. As you can see, there's some faces that have really small area. That's 6 on the power of minus, what is this? Minus 10 to the minus 6. So that's something really close to 0 that you cannot see here, but it's there. And I'm going to curl those faces just first around this area. If you want to use curl the faces that are basically with 0 area. So I'm taking all those polylines. I'm making a list of indexes here. and with the pattern of with the pattern that I get from comparing to this area to 0, if it's equal to 0, that gives me a pattern. I'm dispatching those indexes and I'm deleting the faces from this mesh that are really small and insignificant. And you can see here it has like 160 faces, and after doing this, there are only 96. So that means we just code like 70 faces without actually having the geometry look anything different. So they're there, but you cannot see them. But if when you continue working with it, it might in some point have some trouble with the topology. And after that, you need to weld the vertices, because deleting some of the faces will actually result in some holes. But after deleting, welding the vertices should be fine. And again, you cannot see them here because they're really small, but that's how this component from Millipede works. The topology of it is not really quite good. That's why we need to clean the mesh a little bit before working with it. So after that, we're going to use this mesh again to morph it into some group of twisted boxes that we're going to make. So this time the approach is going to be a little bit different. We're going to use the periodic surfaces and morph them and use them as walls for the actual cell. Not creating spaces with them, but rather surrounding space with those periodic surfaces. So we're going to arrange our twisted boxes setup in a little different way. I'm not going to waste too much time in it because it's a lot of components. It's kind of complicated, but it's not really that complicated. The point is we start with center twisted box. And you need to, when you're dealing with boxes and twisted boxes, you always need to pay attention to the indices of the vertices of those boxes. They need to be ordered in a specific way in order to be recognized as a twisted boxes. So when you make a center twisted box, just a regular box, and you see the indexes of those points, and it's the same if you do a regular box and you see the indexes of those points. But if you do like in Rhino, if you type box and you do like some random box like this, and you input it here, and I'm going to just copy this to see the indexes of those, like the order of the points, it's kind of not the same. So if I try to make twisted box from those corners, it's not going to work quite well. So you need to pay attention to this. Kind of tricky, and sometimes it's messy. So looking for the order of the points is important. That's why we start with creating just a box with the center box too, not box in Rhino, because for some reason the direction of the point is different. So we make the box, and we can bake this box. Then, yeah, so it's baked here, and then we can, if we turn on the control points of the box, we can deform it as we like, and then put the box in a Grasshopper again with some container. Okay, so that's how I did this prep here. I just bake the box, I just deform it, and then you put it again in a Grasshopper. As you can see, the order of the points is the same as the initial point, and that's important because we're going to make twisted box from this geometry. So we are taking this prep now, we are taking the vertices, and we are constructing box from the corners. So that's a twisted box. And then we are using the thickness box component, which makes like offsets the wireframe of the box inwards and makes 6 new boxes from each direction. You can have this parameter here, true or false. That means do you have a box in the middle or not. I don't need the box in the middle, so I keep this whole. And if I bake those now, those are six polysurfaces here. The thing is, I don't need the front one and the back one. I just need those. That's why I bake them. And also what I want to change as well here in this setup is when you put the thickness of the box, like now it's 0.5, it offsets the box in all directions with 0.5. But in the front, where I keep it open, I want to have it not that deep. So I can just turn on the control points of those polysurfaces, and then I'm going to just edit those points a little bit. Maybe like this. Yeah. So just you edit those as you like. That's how we get to this BREP here, which is internalized in your file. We just need to reference this edited geometry here. That's why we get this BREP. And again, that's a BREP. The thing is, you cannot bake twisted boxes, unfortunately. Maybe that's maybe it's possible in Rhinoceros. I haven't tried it yet. If not, it's gonna be nice if you did the twisted boxes there. But you can, if you bake twisted boxes, they're going to be baked as BREPs, not twisted boxes. And then when you put them inside Grasshopper, you can put them inside only as BREPs here, and then make twisted boxes from them. So I'm taking this BREP, and I want to make it to twisted boxes again. So I'm taking each pair of faces here, the outward and inward, and then you need to flip the direction of one of the curves, and then merge them into list of surface here, a list of pairs of surfaces, and then make twisted boxes between each two surfaces, between this one, and then this one, and this one, and so on. So that's this. And now we can use this list of twisted boxes to morph our geometry in this geometry. And again, the mesh that we make. Again, you can play with the orientation of this mesh or the orientation of the bounding box. Like right now is with the XY plane. The thing is that this mesh is quite similar in all directions, so it wouldn't matter much. Sorry. And we morph it into this set of twisted boxes, and that gives us this wall poly mesh that doesn't look like much yet. So we need to refine it a little bit. First, right now there are a list of meshes. We need to join them. We have the vertices and unify the normals, and then unify the normals. Yeah. The thing is, right now, if I smooth this mesh here, like again, I can bake it and make it to sub-D if I want, or just see how it's gonna look by using some Catmull Quark smoothing algorithm. Oh, sorry. Yeah. It's gonna look like this. So from this wall poly mesh, if we smooth it, either with Catmull Quark or make it sub-D, it's going to look something like this. So we're gonna make the walls of the cell with that surface. The thing is, I really don't want to have this curvy edges here at the end of it. Like if I take the naked edges of this here, they are like some weird shape. So if I smooth it, that naked edge here is going to have some curvy shape, and I don't want to have that. I want to have this flat in order to make it easier to close it after that, or treat it like a surface, not like some curved mesh. So we need to refine that mesh a little bit further. And how we do that is we're going to take all those points here that are on the naked edges, and we're going to somehow project them on some plane and then rebuild the mesh with those new points that belong to a plane here, not this curvy line. So we're taking the naked edges, we're taking the points from the control points of those naked edges, and from here, that's the twisted boxes that we morphed, transformed into breps, and we're going to take only the edges, the wireframe of those twisted boxes, and we want to somehow make a plane for the projection of those points that is on this face here. Okay, maybe I didn't explain that quite well, but basically I need to take the corresponding plane for each of those curved naked edges and then project those curves into that plane. So I'm taking the control points and I'm checking which one of them belong to some of the wireframe here by finding the distance to the wireframe and taking only those who have 0 distance here. So that gives me those points from the curve that belong to that wireframe. You see that point, that point, that point, they all belong to the wireframe. And from each 3 of those points, I define a plane. So that's how I get a plane for each face here. And then we can project those naked curves onto those points here. And further, I want to simplify a little bit those naked points with a reduce polyline by removing least significant vertices with certain parameter. This will make those naked edges simpler and not too curvy. So the next step, I want to take that mesh that I want to edit. I'm going to take just the naked points of it here, and I'm going to pull those points onto those new naked flat polylines. And then I'm going to replace those points with the pulled one. I'm going to rebuild, first deconstructing the mesh, and I'm replacing in the list of vertices of the mesh the new points, the old points, the curvy one with the new ones that belong to the flat polyline. And after replacing the points, I'm reconstructing the mesh with the new set of vertices, but the old mesh faces. So this approach is really useful because you can manipulate meshes in many different scenarios like this. Deconstructing the mesh and do something with the vertices as you like, and then construct the mesh with the new vertices, but the old rules for making the faces. And in this case, that transforms this curvy mesh into this mesh that it has the naked edges of it. They're really flat. They're on a flat plane, and they're simplified compared to this one. So right now, if I smooth the mesh, they're going to stay flat, and it's much nicer than the result from the mesh before the refinement. So that's a trick you can use for many cases. Deconstructing the mesh and then replacing the vertices with some new ones that you have modified, and then constructing the mesh again with the new vertices and old rules for the mesh. So that gives us this refined mesh morphed into the twisted boxes. And we can now smooth it a little bit, and we can do some Laplacian smoothing as well, which, like the Weaverbird loop subdivision, increases the subdivisions, but the Laplacian smoothing just relaxes the whole mesh. It doesn't increase the subdivisions. And after that, we can experiment with some mesh mirroring. So we take the mesh and we use the mesh mirror with some XZ plane. You can move the point somehow and see what the results are, and then we can do the same on the other direction with the white Z plane and get into this point here, which is the shell for our cell, basically the structure that represents this. So if I bake this, yeah, so we can put this in some different layer. That's how we get the main structure. So morphing the mesh, a little bit refinement, and then smoothing, and 2 times of mesh mirroring gets us to this point. So from here, there's some things we can add to the geometry. Again, if we offset the mesh, we have the inner and the outer part of the mesh, like in the previous example, but this time we work with meshes. So I can bake this in here, and I can bake the offset. Okay, maybe the opposite. So I'll bake this here. Yeah, after the mesh mirroring, we can smooth it a little bit more with the Catmull Quark algorithm that will also give us quad faces, not triangular faces, and some nice pattern on it. So offset the mesh in certain distance. You can bake, that was the inner part, and that's the outer part of it. Yeah. Okay. So the next steps are this one. The next steps, we can add close those openings here, make the glazing, make the floors, and add the skin to it. So we're going to work with those 2 meshes here as an input for everything else. So first, the skin modeling. It's a similar concept as we did in the previous examples. We're going to use the duo graph here for making this pattern. And we're going to take this, not the quad face mesh from Catmull Quark, because it's going to have to become too small of a pattern. I'm going to use this triangulated mesh here before the Catmull Quark algorithm. And the duo mesh duo, you know already what pattern is going to give us, those hexagon cells. And what really I don't like are those almost circular cells here. So I'm going to dispatch them by measuring the number of control points for each polygon, and I'm going to dispatch the polygons that have more than 8 control points. So that will dispatch those parts here, and I'm going to work with just the rest here, those set of polygons. And like we did before, again, we can scale it with some graph mapper according to the center of each polygon, and we can move it, and the vector for the movement will get from the center of each polygon, and a point projected on the inner mesh. We already been through this a couple of times, so should be familiar by now. So moving them, and then just explode and merge the contours, and then use the mesh waft, which is the heaviest component in this definition. Is going to take a while because there are a lot of faces and therefore a lot of edges to make a waft. So that gives us the waft between the edges, and again the cap of those polygons we do by making a de Launay mesh here, by taking the control points of each polygon and adding the middle point and making a Devolnoy mesh from each list of points. And then we can further smooth it a little bit to make it more like the surface beneath. And then we merge the two parts and we can join them together in one whole mesh, but joining them is going to take a while. So I'm not okay. We can leave it like that. So I'm just going to bake that. That was the skin. Yeah, maybe if you disable the mesh edges preview, it's going to be easier to visualize for the graphic card. Keep that in mind because there are a lot of meshes here. Okay. Bake. Not sure why it doesn't like my command.
Are you trying to make it?
Yeah.
Maybe you have a Rhino command running in the command line.
Okay, so turn off the preview measures because it's getting heavier. And yeah, now we'll be fine. Yeah. Bake it. Okay. I think we got it. Yeah, but actually not gonna keep it because it's hard to visualize and it's getting heavy for the video card at this point. So I'm just going to undo this. Yeah, but you know the result, right? Okay, so we have the skin. So now the next part, we need to model the slab, the glass, the profile, modeling in this thing, and that's kind of it's more of a procedural modeling. It's nothing fancy, but you can find some useful techniques that you can use in different scenarios of your design. So where to start? Maybe, yeah, just let me see. Okay, so maybe we need to close the openings first. If we take the mesh naked edges, that gives us all those openings that we need to close in order to make it a cell, a closed cell. So again, the naked edges might turn on with some really small naked edges when some imperfections in the mesh that we did after the mesh mirroring. So it's good to, just in case, dispatch and kill some of the, like for example here, I'm dispatching some of the naked edges that are less than 2 centimeters or 2 units length because those are probably some really small edges that I don't find. In this case, yeah, they're none, but sometimes you need to watch out for this. Right now we are working with 12 naked edges, like 5 inside and then 5 more outside, and then 2 in the front, 1 in the front and 1 at the back. And I'm going to treat those openings differently. So I'm going to come up with a way to differentiate those and isolate them from the geometry. Like you can always bake them and select them manually, but I don't like this because it breaks my algorithmic approach. If I can, I try to stay in Grasshopper, and unless it takes a lot of time to make algorithm for it. But in this case, we can come up with some really quick rules how to dispatch those curves into different lists that we're going to work with. Like for example, if we want to dispatch those to the front and the back naked curves from the group of curves that we're working in, we can make the bounding boxes for all the curves, and we can check, we can deconstruct their domains and just dispatch the domains that are 0 in the the y direction of it. So if I do the bounding boxes and I deconstruct them and then deconstruct the domains of those bounding boxes and see which, so that will give me the dimensions of each bounding box, in this case in the x direction. So if I sort those curves according to their dimensions in the x directions, the first two here are going to be those with 0 x dimension. So if I split this list in the second item after sorting it, that's going to split it into those here and those here. So with those, I know what I'm going to do. I've decided that I'm going to make this smaller window inside, and I'm going to split it later, and that's going to be part of the glazing system there. So, but I wanted to put it a little further from the front edge inwards to the space inside there. So I need to move them a little bit. In order to do that, okay, I'm using some component of the other logic. So yeah, let's start with the other set of curves here, because those are pretty clear what we're going to do with. The other set of curves here, again, it was this one actually. All the naked edges without the front and the back. So here I want to differentiate them to the ones that are from the outside and the ones that are from the inside. And I'm going to do that by measuring the distance for each curve to this, okay, this bounding geometry. Here I forgot to mention, the same way I did the mirroring of this mesh here, like once and twice, I'm going to do the same mirroring of this this bounding box of the geometry of the same mesh. So once, 2 times, that I'm getting this bounding geometry of this mesh that I'm working with. So if I take this bounding geometry and I measure the distance from each curve to this bounding geometry, obviously I want to have only, that's the component curve nearest object. So I'm measuring the distance, and I want to have only those that have 0 distance between them and this bounding geometry, and that's obviously those on the outside. And the others that have more than 0 distance are the ones from the inside. So that's how I differentiate between the sets of curves here. So from the ones that are inside, this one on the top, I want to have it as a lightning ceiling, let's say, and it's different from the others because it's not flat, it's not planar, but it's a result of the mirroring. So if I test which of those curves are planar, that will give me a pattern how to dispatch those from this one. And I can just patch this curve with the surface, and then I'll bake this into some layer that I'm going to make a lightning ceiling from it. I don't know which one. So I'm just going to bake this because I'm done with it. So that's, let's say, the lightning there. And the other 4 sets of curves, those are the one inside. I can differentiate them by taking the one at the bottom and the one at the top, the same way I used as logic like before with their bounding boxes, but this time I'm comparing their Z domain. So I'm getting just those that have 0 Z domain here. So those are this one, and those are the ones on the walls. Those I can just bake as glass in some point. Okay, let's just make it a boundary, and that's easy because you already make sure that all those naked lines are projected onto the planes. So I'm sure this boundary component is going to work just fine. I can bake those into glass. And for those in the bottom here, I will also bake them as glass, but like a glass flooring. But I also want to make this part between them like the floor in the cell. So I want to have them as glass flooring, and I want to have this space between them as solid floor. So I'm going to take them here. I'm going to use the bounding rectangle component, which will make a rectangle around them. And then I can make a region difference between this bounding rectangle and those 2 polygons. And that will give me this surface that I can just easily extrude, and I can bake it in some. That will be my solid 4. Which one was it? Okay, maybe let's just make it here. And those here, I'm going to want to leave them as glass because they're connected with the outside of the cell here, because the periodic surface, that's the periodic surfaces topology. Where was it? Yeah. So this I'm going to bake into glass or slabs again, whatever. Okay. Now I've covered all the openings on the inside. We need to go back now. Yeah, now we can do the front and the back, the back glazing. So if I do the bounding box of the floorings and the walls, that's gonna give me the two planes that are the closest to the existing flooring. So I want to move those curves inwards, but I don't want to move them more than to this plane, because they're going to interact with the floor that I just made. So that's why I take the bounding box of the floor and I just take those 2 planes of it, and I'm going to project those naked planes into those, and I'm going then just to scale it with a constant factor, and I'm going to make waft between those outer and inner curves, and that's going to give me this part here of the design, this framing. So I can bake this again, and I can make from this inner part, I can easily make it a boundary and then bake it into the glass layer. Okay. So next comes all the openings that are on the outside here from this patch here. I get all the curves that are from the outside, and I want to do similar things with them like I did with this front glass. But this time I'm going to move the glass to the other direction, not inwards, but outwards. So I'm evaluating, because they're planar, I can use evaluate surface, and it's going to give me a normal, a perpendicular to this surface, which I can use for moving them outwards, and I can offset them a little bit, and then when I move this, yeah, okay. So move them, offset, one more offset, and then make some lofts here. Well, I don't want to go really deep into it because that's some really subjective things. That's a part of my design. I decided to that way, but the point you want to get is like we're taking those curves and just we're offsetting it a little bit, and we're moving in some direction in order to make this those framings here, and we can bake that again. Yeah, here I've decided to, yeah, maybe not. I don't need this one. Yeah, so bake that, and then again I can do easily just the boundary here in some point and bake it into the glass. There you go. I'm gonna unhide everything, huh? Okay. Bake that too. Yeah, so we make the walls with the surfaces, and then we closed all the holes with glazing. And one last thing is we need to make those those framings in order to make it more architecture, because it doesn't make sense to leave it as one big piece of glass. Here's a few tricks here to use. Like we take all the surfaces that we use as glass as a whole, then we untrim those. In order to work with untrimmed surfaces, we can divide it in the U and V direction, like 4 divisions in the U, and you can just keep 1 in V. And that gives us lines that can divide the surface, and we trim those curves with the shapes of the glasses here, and you can just make them into a mesh pipes and say that's the metal, that's the glass framing here. So untrim the surface, divide surface, make lines, trim the lines with the contour of the glass, and then just make mesh pipes. And you can keep the segments as 4 because we don't really need it as circular, but rather rectangular framing. And you can take this outer framing of the glass, offset a little bit again, merge the two, make a boundary, and extrude. Those are some pretty basic, like solid components that are pretty straightforward. And then just bake that too. Yeah. And the only thing I'm missing is the skin that I made somewhere here. Yeah. And yeah, that's the result from this algorithm. So to recap, maybe how we get here again. We started with this simple periodic surface, and we keep it with really raw resolution. We cleaned the mesh a little bit by deleting some of the faces that have really small area, and then we welded it. And on the other hand, we did some operations with about the creating the twisted boxes by starting with a simple box, then editing it a little bit, then we make a twisted box, thick and twisted box, and we use those twisted boxes to morph. Like yeah, we did it a little bit again. We rebuild it with bases the outer and the inner shell of it, and we use those to create again that layer of twisted boxes around this space inside, and that we use for morphing the whole poly mesh from the beginning. Then we join, we weld, we unify the normals, and we flatten the naked edges of the mesh in order to have planar openings on the outside. We do that by projecting the naked points of the mesh on planes that we created on the outside of the twisted boxes, and then we rebuild the mesh with the new projected naked points. Then we smoothen the mesh with Catmull quark and Laplacian smoothing. We mirror once in the XZ direction, and then again on the YZ direction, and that's the mesh that we are working with after that. So from there, we offset the mesh, so we create the inner and the outer layer of the cell, and we start to close the space inside by adding glazing and framing on it. Also, we work with the outer mesh. We create some skin pattern using Weaverbird dual graph algorithm. We scale the polygons according to some rules we make with the graph mapper. We extrude them a little bit, and then we make meshes from all of it in order to put a skin on the outer shape of it. So we're really deep into our 5 hours together. I think we have something like 20 minutes left. I can answer some questions from any of the chapters that we went through.
Hey, Radul.
Yep.
Thanks. Let's see here. Do you want to maybe stop sharing for a second? We can go to cameras, and then we can share again.
Okay.
Let's see. Actually, I wanted to point out something that I forgot I even made.
Sorry?
I wanted to point out something that I forgot that I made for one of the things. So I'm just going to share real quick my screen. So at this part here where you like made this box and then baked it, I actually have this component that I forgot about in Pufferfish called reference twisted box, and it will make a twisted box based on the point order of like the way a box is in Rhino.
Exactly what we're missing. That will save like 10 components in that definition.
Yeah. I just wanted to point out that it's there. I mean, I forgot that I made it. So
I was gonna say that there's probably an easier way to do everything that I did there, and if somebody managed to come up with something, I'm sure there is a quicker way. But I did it once, and after that, I was kind of lazy to try to make it. But you've done the work already, I can see. Yeah.
Stop. Okay, so let's see. Seems people are liking this. Let's see here. First of all, does anyone want to ask a question? If they want to come on camera or voice and ask a question, just raise your hand. In the with the raise hand buttons, and we'll bring you on either voice or camera, and you can ask a question or discuss something if you have in mind. Or if you want, you can just write in the Q&A area. So there's some stuff in Q&A. I don't know if we have.
Okay, I'll answer some. Where did you find the bottleneck navigator? That's from MetaHopper plugin. It's additional plugin. It's not native for Grasshopper. It's really useful. You should check that out.
Let's see. I have someone here who wants to come and chat.
The transition of the glass.
Esteban.
Yeah.
Hello.
Hello, Esteban.
Hey.
Hi guys. Thanks for running the workshop. I just had just one simple question from the beginning of the workshop regarding the mathematical equations that were used to create some of the initial surfaces.
Yeah.
I was wondering where you can find those, if those are equations you guys are generating yourselves. And
no, it's a good question actually. I found them somewhere on the Grasshopper forums, and I really tried to find them again in order to give credit for the guy who shared them, but I really couldn't. It was in some definitions, and from there I just copied them from file to file, and I tried to look in them in the internet from some mathematical forums and stuff. I really couldn't find it anywhere else except the Grasshopper forum. So somebody did those, and I'm just copying them for a few years now. And
you want to maybe share your screen again?
So yeah.
Just so they can know what we're talking about. Yeah.
So they were in some definition in a Grasshopper forum that was doing some periodic surfaces, and on twisted boxes actually as well. And I tried to find some mathematical publications with those, and I really couldn't anywhere. But those are quite a lot actually. It's like they're more than 15, and I tried to look at them at this website that I send you, but they're not doing it like that. They're using some custom-made evolver, and it's kind of really old. So if you don't try to look at them in the website that I sent, I've tried that many times. They're not there.
Okay, and are all of those equations working as one when you connect them all to that component?
No, they're not working as one. That's just a filter gate. I'm just changing which one I'm using with a simple input here. So
okay.
it's always just one from outside here.
Wow. So there's 25 different options that.
Yeah, exactly.
Wow.
So yeah, you can try. By the way, also something I forgot to mention. There's some other periodic surfaces here in the Mesh Plus, I think. Yeah, here in the Mesh Plus volume. Those are also periodic surfaces. Like for example, the butt-wing is really useful because there is not an equation for the butt-wing here, and it's really nice actually. Check. What can I gonna make it somewhere? But yeah, check this out. You can really easily use the butt-wing and any of those here, and those are meshes. Those are like low poly meshes. You can use them as they are, mold them into twisted boxes, and then follow the workflow by joining, welding, and smoothing here.
Okay,
but
awesome.
Those
Thank
are different
you guys.
options. Yeah, you're welcome.
Appreciate it.
Thank you. Oh, we have more people that want to come. Let's bring someone else. Okay, I have Ramsey coming in. It might require your screen also. pending.
Hello?
Ramsey, are you there?
Can you hear me? Hello?
Yeah, hello.
Yeah, we hear you.
Okay, sorry, I don't know what happened. I'm just saying hello. Anyway, I don't know if you guys can see me. I'm trying to turn my camera on, but it's not working. I apologize.
Okay.
First of all, thank you for doing this. And also, I think I like the form where the definitions are ready. That's saves us a lot of time, I think, and able to cover more. But so anyway, thank you for doing it this way. It's kind of different, but I appreciate it. I had a question with the second exercise, Grasshopper, called the file, I think it's mesh.
Yeah.
With the paneling, I noticed when you were doing it on your screen, the paneling showed, you know, it was offset from the surfaces, but I'm getting some intersection. So the first paneling and the last, they were intersecting with the gray and brown surfaces in the and it's the same file. I used your file, so I was wondering if there's something I need to fix. Maybe I need to offset it, or.
Okay, I'm just gonna share the screen again. So first of all, make sure you disable those render objects here, so you hide all. Because sometimes if they're still working, go and look at some mesh here, and that's different mesh from the quad mesh that I did. Like, it's because this mesh, when you smoothen it with Weaverbird subdivision, and then use the Laplacian smoothing, it changes the shape a little bit, like it relaxes it. So it's not quite the same.
Yeah, I think I used the last surface, the surface
Yeah.
that has the custom
This one?
preview. No, not that one. The ones with the shading, the color swatches. Oh, okay. I used the very top one, not that one.
Yeah,
The
make
very
sure you
first.
disable those, because you might be looking at the rectangular surface here, a mesh here, and then if you try to look at this, the quad mesh, it relaxes in different way because they're quads, not triangles. So it's kind of the same, but not really. It might looks like they're intersecting, but they're actually different meshes. If that's something that you're getting, I'm not sure.
No, if you look at the very first set of color swatches, the top three on the right side.
Yeah.
Yeah, those are the ones I previewed. So I was using those.
Mm-hmm.
And
Yeah,
that's where I was getting the intersection.
Okay.
Okay, so is that the wrong ones?
Yeah, probably.
Okay.
Do you want to share your screen, Ramsey?
Yeah, I could do that. Share screen. All right, here we go. All right, let me know if you guys can see it.
Yeah, we see it.
Okay, the Rhino file.
Yeah.
Okay,
Yeah.
so this preview, this geometry is those three.
Yeah.
And then I baked the first one, and I'm getting, see how I'm getting some intersections here.
Well, you're baking a different one, I think. That's that's made from the quad surface. That's why it's different. And the one that is previewing, it's made from the triangular surface.
Yeah.
I baked this guy right here, the first one. Yeah. So I wasn't supposed to bake this one. Is that what happened?
Well, you're previewing.
Yeah, just turn off the preview, because
you're previewing the triangular meshes, but baking panels that are made with the quad mesh. That's the problem.
Yeah.
I see. Okay. Okay, I think I get what you're saying. All right, so that's why I was looking at the wrong surfaces.
Yeah, you're just previewing the triangulated one before
before
they were quadded.
Okay, I see. I kind of stepped away. I'm sorry.
So you're going to teach now for the next hour, yeah?
Yeah, sure. Next time. But I kind of stepped away the last 40 minutes. I had to go take care of something. But when I got back, I saw the exercise. Is there any way you can use that that form that you had to follow, like a BREP, or like can you use it to follow a shape of a volume?
Sorry, can you
Does that
repeat
make
that?
sense? So the I don't know if you want to share your screen or I can try to open it. But the last exercise you just did.
Maybe you're better for Radul to share. If you know.
Yeah, I don't have the file, but because I was just watching, I didn't participate in it. But the last geometry you showed, I was just wondering if you could take those minimal surfaces and have them pretty much you map out a form, whether it's a BREP or something, but then you have it follow that volume, the volume of your mesh or your BREP. And then you have those minimal surfaces.
You could, I mean, the only good way to do that would be like really to like edit it in Rhino, like cage edit it or deform it in some way.
Okay.
Because there's not really a great way to like morph to kind of I don't know, random geometry, like because there could be any set of rules or I don't know. Radul, what do you think?
I don't think I understood the question that well.
He's basically asking like, can this shape be deformed into another shape? Like it doesn't have to be in this kind of like
like we did before with the wall poly mesh that we baked and edit and enter to sub-D.
Yeah, like you could deform it, I think, in any way and just bring it back in.
Yeah, you can just bake the wall poly mesh and then do whatever you like with the control points and then turn it to sub-D or make it to mesh or whatever.
Yeah.
Okay. All right.
Yeah, there's no like simple, because again, there's no like single rule that would do that. So it would be more like
you basically need to work with the
want.
wall poly mesh before tessellating it, smoothing it, and then
okay,
because you can always smooth it whatever you do.
Yeah. Okay. I did kind of miss most of it, but when I saw this shape, I automatically thought about it would be great if I could take this form and instead of following like this cube, it follows another volume or another shape. But
you can make another rule for getting into that shape. Right now, I just make this twisted, not twisted, but tilted cube, and then I mirrored it. That's why you're getting. If you come up with some other rule for it, of course, it's okay. All how you model. You need to think of different ways to model a space and then fill it with twisted boxes, and you're there.
All right, great, thank you. I'll mess with it and submit some posts hopefully. But again, thank you so much, you two. I appreciate it. Zymorphine rocks.
Thanks, man.
Thank you.
All right, guys.
Bye. Okay, we have another one. Let's come here. Berlin. Let's bring Berlin in here.
Yeah, hello.
Hi.
Hello.
Hi. Thanks a lot for a learningful webinar. I had a question rather around the architecture part of designing like this. And I was wondering if you have any thoughts on how to confront clients with designs like this, and also what would you propose as a construction principle for such kind of architecture designs?
Okay, so for the construction principle, I'll start from there. Obviously, those the periodic surfaces in general are pretty good with 3D printing because they're continuous and you can easily 3D print it and apply 3D printed principles on them. So that's one point. And the other is obviously digital fabrication and panelizing, and you know how that works. The hard part is selling this to the client. I know the struggle. You know, this is still really avant-garde. It's like on the edge of architecture. It's half an art, like still, and not exactly architecture, because it's not like you can actually build it tomorrow or something like that. But I think it's important to expand our thinking into those directions, because you never know what's next. And maybe in this point, it's still hard to design stuff on commercial basis like that. But from the research point of view and from artistical point of view, I think it really helps. And maybe you won't build this design, but maybe somebody is gonna like the way you're thinking, and it's going to work with you, and you're gonna get closer to the reality together. I don't know if that answers your question, but it's a good one. And you know, it's hard to work with clients with those designs, but I think we need to push as much as we can.
Yeah,
and see where it comes.
I
And
agree.
it's not impossible either. I mean, you see people doing it, right? It's not common.
Yeah,
as
it's rare,
common, but it's not impossible.
You never know who you're talking with, basically.
Yes, and a short other question. That was just about the renderings you showed about the designs. You said you've done some of them in Keyshot. Where was everything done in Keyshot there?
Yeah, everything is done in Keyshot, and of course some post-production.
Cool. Thanks a lot.
Welcome.
You're welcome. Let's see. I got another one. You're very popular today. We have Jonathan coming in.
Hey there, thanks for
Hi.
Can you hear me all right?
Yep.
Okay, cool. Thanks for the webinar. This has been helpful. Definitely picked up some tricks along the way. One thing that has always perplexed me a bit when dealing kind of with this more computational design and these very abstract design solutions is, I'm going to take a back step real quick. I've heard a good way of thinking through Grasshopper is like baking a cake, where it's like, in order to like have the recipe fully work, you kind of have to have a picture also of like what things do and what you are going to see in the end, because then you can like chain what you need to together in order to kind of create and explore a bit. So I guess when you think of these shapes and writing these scripts, like how far in the future are you kind of thinking of the design, and how much of it is like something you kind of find out along the way or explore the shape and then kind of like tinker with it a bit and then keep going? Like, how, yeah, I guess that's just.
Well, I get it. That's a great question, actually. Answer is not a lot. I'm not actually seeing what is going to turn out at the end. I just look for some things, like there's always this design thinking you need to, when you're doing whatever you're doing, like any shape, there's always this part of your design thinking that it tries to make a good looking shape. You're not actually sure what you're going to use that shape for, but the first thing you're thinking is it needs to be good looking shape. And then you explore different routes for the algorithm, and you try different approaches. And for me, until some point, I'm not actually sure where it's gonna come up, but I'm trying to take one step by another. Like when I get to a shape that I really like the general shape, like let's say the periodic surfaces, I morph them in some silhouette or some general shape. I stick with it and then try to expand on that, to try to work on the details on that. And then when when I see something I like, I stick with that and I go to the next level. But it's not like I really see what really far away what is going to be. And the other point is that I explore a lot of different directions for that. Like here, I show you those scripts for like 4 or 5 hours. It really took me like 20 or 30 to do them. Maybe more. I don't know. It's not like I had a lot, but the things that I'm showing, they're really condensed. Like I'm at the end of the process, I'm deleting most of the stuff that I do. I'm arranging the whole definitions in order to be easier to read, and a lot of the things that I'm trying around the way, you guys, you don't see them. You just see a really condensed result at the end.
Right. Okay, thank you. That was helpful.
Thank you.
Thank you.
Okay, we have Andrew coming in.
Hey guys,
Hey.
thank you very much for this. I wanted to ask a question about the very first periodic surface Grasshopper script. So you gave us 25 of these mathematical meshes. What I'm curious about is what's I think you initially used number 7 or number 5. I don't remember exactly. But if I if I choose one of the 25 meshes and I apply it to, like, what would I be doing? I would be applying it to the mesh, just the first mesh that starts the second script under. I don't know how to explain it. Unfortunately, I'm zooming from a different computer, so I can't share my screen.
You mean
But,
can I use the other algorithms to make it the mesh from any mesh from mesh to NURBS?
yeah, more or less that's my question.
No, not really. It's kind of similar sometimes, but that's why I try to explain the logic behind it. It usually takes different approach for the different meshes, because you need to look at the mesh and there's some creative thinking about it. Like you need to see which parts are repeating themselves, which part you need to mirror and rotate. There's not a universal algorithm that you can, at least I haven't done it, that you can turn any of those 20 meshes into NURBS. And I really tried, actually. Like I did algorithms for 4 or 5 of those, and then it took me a lot of time to simplify them in this manner. In the beginning was really more complicated to turn the mesh into the NURBS, and that's the best that I got. And it really took me some time to do those two, actually. But they're really kind of similar, because you're cutting the initial mesh into some parts and that you're working easier with. And the second and the third definition they're like the same 90% of them. So there are some similarities. If you go through the other meshes, you might find some pattern that you can use, but I guess you still need to approach it different for different meshes.
Right.
The other way is the Rhino 7 has this really cool sub-D, from meshes now that you can use. The thing is, I'd like to do it that way because I have more control on the topology at the end.
So I was just gonna say, like Rhino 7 has different options like packing faces to make bigger NURBS, but the problem is like it's pretty unlikely that it will know how to pack the surface, because the way it's packing surface is just looking for like kind of like adjacency and continuity, but that continuity doesn't necessarily mean that's where you would break things up, for instance, for panelization or construction in real life. So you could obviously automate it, like brute force automate it in those ways, but likely you'll end up having to split it a different way depending on like what actually needs to be done with it.
I see. Yeah, because I tried to replace some meshes with one of the 25 options. It didn't go well for me.
No.
Thank you. Anyways, thank you. Great webinar.
Thank you.
Thanks.
Okay. Do we have anyone else that wants to ask a question? I saw a hand up here, but it went away. Oh, there it is. We have Yannick coming in.
Hello, guys.
Hey, how are you?
Hi.
Hello. So thanks a lot for the webinar. It was great. I learned a lot. And I have like not the similar question like the guy before, but I have the question if there's any possibility to not use like this periodic surfaces. So I watched also not the last seminar, the webinar before Christmas, the free webinar. Don't remember the name. I think Dreamflake or something like this. And we used like Maya to also generate some stuff with these twisted boxes. So is it also like, do you think it's also a way to not use these periodic surfaces? Because I think if you always use them, or like in this webinar, we only use these periodic surfaces, and I want to be like independent from them or use something else. Is there any?
Just replace the mesh with a different mesh. I mean, honestly, like you can go from mesh to sub-D to NURBS in any geometry you want. The nice thing about periodic surface is like they're you know, because they're like mathematical, they're just like, you can think about them as easier to construct and easier to identify as structural, you know, in my opinion. But they could be whatever you want, you know. But chances are, if you do something in Maya or this, the thing might change dramatically, like to be able to be constructed, depending on your geometry and curvature. It's just the nice thing about periodic surfaces is that you can measure them and document them in an expected way, in an accurate way, because they're mathematical. But yeah, I mean, if you took the Dreamflake webinar, like you can do the same thing there, just replace it with something else.
Okay, thanks a lot.
Radul, do you have anything to?
The principle with Maya is the same. It's still low poly modeling, and actually one of the examples we did, the one we use in the second chapter, it's not a mathematical periodic surface. You construct it by yourself. You can use that principle. So anything you can do that repeats itself in 2 or 3 dimensions, you can use. The other ones are actually the difference. They're minimal periodic surfaces, not only periodic, but they're also minimal surfaces, and they're mathematical. But the one that we're using for the chapter 2, the MeshEdit, it's not actually defined by mathematical formula. It's in the first file, the 3rd definition, I think. There you construct it from another setup, from the truncated octahedron. So in the same way, you can do it with any other geometries. You can explore some by yourself, maybe some export them already. So it's not necessary to use it as a mathematical equation.
Okay, thanks a lot. It was really helpful. Thank you, guys.
Okay. So we have some questions here. Walter is asking, how is contorted composition similar to what would be incorporated in the corpuscle chapter of the master's class? And for me, I like, just to put it simply so that we're not here talking all day, I mean, that whole chapter is about designing a living cell, or the new kind of living topology for people. So we'll be exploring different ways computationally to develop new types of I guess you can say like housing unit. And of course, even much more detailed than this. And this is just one way with this kind of minimal surface. That's what that whole units chapter is about at that scale.
Yeah, I kind of expanded on that because I didn't use only like a living topology, but more like a pavilion-like structures as well. But yeah, what Mike says covers it all pretty much.
We have a question. Are there any Greece files that we need down for tomorrow? Which I don't really understand because there's nothing. If you're going to be here tomorrow, I won't be here. So let me know how. No, yeah, I don't know. Maybe there's some confusion, but there's nothing. There's nothing tomorrow. Yeah. Let's see. How to apply those meshes made from the expression to other files. I think we just talked about that, right? Or maybe Alexandra is asking, like, could you use those expressions to generate a different, like, can you use it directly to generate the surface or?
No, not really.
There are some equations you can use to generate surfaces, but they're usually simpler.
Yeah, the one I
because
showed with the
surface is
two-dimensional
limited,
surfaces.
Yeah.
There's a plugin, I think it's made by the same people that did the Millipede that use volumetric modeling, and you can plug the equations there and gives you like a volume of it, but it's still some kind of mesh. I haven't tried it, but it's still meshing it, the result.
Here. There's one about the Weaver loop, like that 2 consecutive edges, 1 and 0, have same value. So this is a common Weaverbird error. And what the error basically means is that you have 2 edges on top of each other. And you can usually get rid of that by welding. And in Pufferfish, you have the rebuild mesh component. If you use the last input, there's weld and set tolerance to something like 0.01. That usually clears it up for me. But that's basically what that means, is that for some reason you have, your mesh is having edges on top of each other. In the 2 surface depth, you're using a lot. I like curve seams after merge and close curves. I want to create a straight loft after that instead of a twisted one, but I can't find a way to do so. How would you solve this?
Well, isn't it working in my definition? I don't quite understand.
Create a straight loft after that instead of a twisted one. Yeah, I'm not sure.
Okay.
You understand it?
I think I do. I think I did that in the definition. I'm not sure why the person is not. So basically, here, when you have the curves, just a second. Yeah, when you merge the curves here, at the end they have some different starting point, and they may be some in the different direction. That's why you need to do the align curve first in order to align the starting points. And just in case, then you need to flip the curves with one of the curves as a guiding one, the first or the second, to make sure that they're in the same direction. And then you waft. Maybe if you haven't flipped the curves, yeah, it will give you some bad results. So right now the seams are aligned, but probably some of the curves are with opposite directions. That's why you need to flip the curves with one of the guiding curves first.
Does that answer your question? Or if not, do you want to share your screen? Maybe I'm just going to bring them on to share their screen. Easier that way than trying to guess.
Hello.
Hey, bro. Yeah.
Hey, how are you?
All right, fine. I'm gonna
Feel
try
free to share.
now. Thanks. I know it's a bit tricky as a question, but maybe I'm too tired to solve this right now.
Okay.
Screen.
But did they understand the question, right?
Yeah, but it's the different part of the.
Okay.
Can you check that right now? Yeah.
Yeah, we
Yeah,
see
yeah.
it.
All right. It's actually right here, and as you can see, this loft right there, it's like twisting this.
Yeah, it's because you need to give it like a guide point, I think.
Right
Yeah.
here.
Yeah.
All right. Okay.
Maybe. I don't know. That's
Well-
Michael's component. He should know better, actually.
Okay. And where could I get
Is
that?
this part of your definition, Radul, or did you add this?
I actually, I've been modifying it, so I don't know if I
Okay.
It's
actually.
kind of my part. So just from the
I
first.
think the problem is, can you hover over the C input of output of post curve to see how the data structure is?
From here.
Yeah, up. No, the C.
Okay, yeah, you're right.
Do you need a panel?
Yeah, maybe put a panel. It looks like it's weird.
I think you haven't merged the geometries in the right way.
Yeah, see, they're all by themselves. That's why.
Right.
So it's like lofting only one thing to itself. See how they're all in separate lists there?
Or maybe like.
And I'm actually not even sure how the loft is even working.
Yeah, that's that's astonishing. You need to see what's before the merge.
Yeah.
Fix something before the merge.
Yeah, because they should be in list as couples. They should be as twos. That's
Yeah.
why that's why the seams aren't aligning, because it's looking at each curve individually and has nothing to align to, because they're all in their own list.
Yeah, exactly. Yeah.
But I honestly have no idea how the loft is working, which is
All
weird
right.
to me. But that's
No
why
problem.
that's why the alignment isn't working, because they're not merged.
Yeah,
Actually, I
it's
wouldn't use merge there.
Switching one step.
Do this.
forward.
Get a weave component.
This one here.
Yeah, and graft the two inputs. So graft 0 and 1. And use that the same way you're using merge instead of the merge. Like plug the same stuff in there. So in 0 and 1, forget what P, yeah.
Okay.
Just plug
Replacing
it
this
in.
one.
Yeah, just try that real quick.
All right. So let's go here and here.
Let's look at the output list. Yeah, see, that's how we want it. So that should work.
Okay. Not crashing, fortunately.
So now they're aligned.
Yeah.
It seems.
What's happening with the loft here? Well, actually, that's now a bit farther than the previous one, but I think that could solve the thing. Yeah, I'm gonna try different.
Now the other problem I can see
Whoa.
here. Yeah, so I see another problem is that some of your close curve. Yeah. They're already closed, right?
Yeah, seems to be. Yeah.
I'm just trying to think with the. Yeah, there's something there. But you might be able to just put that into loft, and with the loft options, do the align
From here to
the loft.
All right.
No, you need to align the seams first.
But I think when they're that close,
Yeah,
I don't know what's going on there.
let's try
It's something with the curves, because I mean, even just bypassing. Well, if you want, you can
I'm
send me
pretty
the
sure I have
file.
the close there for a reason. I know it's not closing all of them, but maybe some.
Okay.
Yeah, let's check what's. Well, no, that's doing nothing. Yeah.
Yeah.
I will try to
Weird.
figure out. No
But
worries.
you can send it also, and we can look at it too if you want to send it an email.
Yeah, it's
Okay.
something in a data management, I guess, before that needs to be fixed.
All right. Yeah, I will send you that and we'll try to
Yeah.
figure it out. Probably I'm too tired to find it.
Yeah.
No worries.
Thank you, guys.
Thank
You're
you.
welcome.
Bye.
Okay.
Okay, leave. Okay, fine. Awesome.
I don't know what happened there. All right. So I think we answered that. Bottleneck navigator, you answered that. That was in MetaHopper. Someone's asking how to make the transition of the color at the glass. I think that was just your rendering material, no?
I covered that. It's from the rendering material in the key shot.
Oh, okay. All right. So I mean, everything else looks like stuff we've already answered. If not,
Suggest interesting books for online resources. Of course, there's the forum and the Bible. Like you said, it's the Arturo Tedeschi's AAD. So the white book.
Yeah.
If you're a beginner, that's the thing you need to start with.
Yeah. So yeah, I think that's it.
Okay.
Thank you all for attending and dealing with some of the technical difficulties. We're at a weird moment where Rhino transitioned to 7, but 6 is still valid, and 6 does some things better because 7 has some bugs, but 7 has some features that 6 doesn't. So, and everyone's still trying to update plugins here and there. So, it's a weird time for Grasshopper webinars anytime there's a Rhino change. So thank you for bearing with all that. If you still have further questions about like your plugin wasn't working, just reach out to us, info@zymorphing.com, and we'll try to help you best that I can. Aside from that, really awesome webinar, Radul. I think it was really informative and a lot of fun, a lot of tricks to learn. And I suggest everyone go back to the recordings, just be patient with it, look at your definitions, component by component, see what's happening, try to understand what's happening, like kind of, just go through each component, turn it on, see what it's doing, turn it off. Yeah.
Okay, I hope you guys liked it. And I hope I'll see you again. That's for tonight.
Thank you all.
Thank
Bye.
you. Bye.
Oh, and you'll get the recording after, when it's finished being processed by Zoom. The recording will be emailed. Okay.
Okay. Bye, guys.
Bye.